outset, I, Atya, express a warm welcome to the 14th International Conference, Confluence 2024, Cloud Computing and Data Science and Engineering, organized by Department of Computer Science and Engineering, Amity School of Engineering and Technology, Amity University, Uttar Pradesh, Noida. As one of the leading global universities, Amity University is dedicated towards its responsibility of imparting its students with strong foundation and a platform for the empirical inquisition. With this agenda, Confluence 2024 intends to bring together professional academicians, industry experts, researchers, and enthusiasts to discuss various emerging trends and innovations, share research ideas, and new direction in the field of next generation technologies. Now, may I invite Dr. Dolly Sharma, Professor Department CSE, Amity University, Noida, to present a sapling to our esteemed keynote speaker, Professor Dr. Arun K. Somani, Distinguished Professor and Senior Associate Dean, College of Engineering, Iowa State University, USA.
It's an honor to present you the Tulsi sapling on the online mode. Thank you, sir. Thank you for being here.
Thank you.
It's a great privilege and honor to have amongst us Professor Dr. Arun K. Somani, Senior Associate Dean, College of Engineering, Iowa State of University, USA. Professor Arun Somani received a BE Honours degree in Electronics Engineering from Birla Institute of Technology and Science, Pilani in 1973, and M.Tech in Computer Science from IIT in 1979, and an MSEE in Electrical Engineering from McGill University in 1983. In 1985, after completing his PhD at McGill University, he joined the Faculty of Electrical and Computer Engineering Department at University of Washington, serving
Yes,
as
I'm ready.
assistant professor from 1985 to 1990, associate professor from 1990 to 1995, and professor till 1997. In 1997, he joined the Electrical and Computer Engineering Department at Iowa State University. He served as David C. Nicholas Professor of Electrical and Computer Engineering from 1997 to 2002. Jerry R. Jenkins Endowed Chair Professor for Electrical and Computer Engineering from 2002 to 2014. Director of Information Infrastructure Institute from 2002 to 2015, and Chair of Electrical and Computer Engineering Department from 2003 to 2010. He is serving as Anson Marston Distinguished Professor since 2007, Associate Dean for Research of College of Engineering since 2013, and Philip and Virginia Sproul Professor since 2014. All the Iowa State University. During 2010 to 2011, Somani served as Ram Rajendra Malhotra Professor at Indian Institute of Technology. He also served as an honorary distinguished professor at National Taiwan University of Science and Technology, Taiwan Tech, since 2010, and a visiting professor at Gujarat Technological University. Professor Somani also is serving as a Fulbright specialist from 2019 to 2024. Now, I invite our keynote speaker to address the audience. Please, sir.
Thank you. And thank you for that long introduction. Can I share my screen here?
Yes, sir.
Can you see the screen?
No, sir, it's not shared.
Let's see what we can. about now?
Yes, sir.
So thank you for that long introduction, and I'll try to present a talk on how to develop faster AI solutions, and we'll try to hopefully finish in time. This presentation is essentially based on the research work done by one of the former PhD student, Dr. Krishna Chetty Venkata, and a current PhD student, Dr. Iming Bian. It's a combination of things, and these are the problems we have been working on for a while. So I'll start with, this is the headquarters of Iowa State University College of Engineering. And this is one of the most expensive pictures we have taken in history of photography. And the primary reason was that this building is all automated on the lights. So every light will go off if there's nobody in the room. And in order to keep all the lights on, we have to really put people in the room so that they can keep the lights on. So really using the phrase, keeping the lights on. Anyway, this is College of Engineering headquarters and Iowa State University. If you're not visited here, I invite you to visit the place. So this talk is about finding faster AI solutions. And the reason is that we know AI is everywhere. Deep learning is everywhere. We are all into it, deeply into it. And I'm not going to, it doesn't need introduction any further. So I'm going to leave all the application areas. But in the end, what we want to do is to find a network which can take some data and give us the desired result. And in order to reach those results, we have a variety of platforms available to us, which is computing platform. And depending on the need of the user, these models need to work on a different system. So it could be an edge computing, could be a high performance single CPU, or a data center. Together, the idea is to find a solution. So you have to match the model you develop for the AI application and the hardware combination. And that's where the challenge comes, is that how do you find a solution which is faster, which will work for us. So I like to motivate the problem why we need this faster solution using an example. And the example I'm going to take here is that of cancers. So when you're detecting, this is one of the applications where AI solutions can help a lot. Why is important? Because if you look at the number of cancers which are spreading, fastest rate for the growth, the left chart gives you the thing, and the female breast cancer is one of the highest rated disease which need to be solved. And that solution I'll talk to in the next slide. And this right side is telling you what the death rate is because of variety of cancers. And female breast cancer is number 2 on the rate. So one thing to note here is that they're spreading very fast and the deaths are at number 2. And this suggests that there's some possibilities of curing it better, faster. But what is needed for that is the key question. It's also established that if you look at where the cancer survival rate comes from, if you can detect the cancer at the localized stage, then you have the highest possibility of the survival rate. Survival rate in the cancer world is counted as how many people survived after 5 years of detection. So localized cancer is easier to treat, and the survival rate goes up quite a bit. How do you detect that quickly locally? And that typically is done through the ultrasound images. So basically, you will take the ultrasound image of the breast, and then you are going to review it and identify if there's a cancerous cell present in there. Typically, the diagnosis is done by a radiologist in their evaluation, and then they use sometimes computer-aided diagnosis here. So radiologists have the expertise to do it, but the goal here is to make it automated using AI solutions, and we like to do it with the CAD solutions faster. That's the application in this case. So how do we do that? Well, in order to do the CAD system to work, you need some kind of a backbone neural architecture, and several of them have been developed for the image processing application. And there's a variety of them. I'm not going to get into details of this. And this is a list of some of the most prominently used application area. But that's the one challenge, that what model you can use it, and there are many of them. Some of them work better in some situation, others work better in other situation. You still need a better solution. Then you have the data scarcity. So even if you have the model, you cannot train them well because enough data is not available for a variety of reasons. The data exists, but getting them at one place and training your model is a harder problem. So people use data augmentation technique, oversampling, and things like that. And the third issue in this CAD system design is about the low image quality. So how do you denoise the data? This data is essentially noisy because you're taking an image in an environment which is not very friendly to the image quality. So how do people approach that problem? They look for how can we do the denoising techniques. That means first take the image and try to pre-process it. And it's done using a variety of filter mechanisms. And there are again a large number of different filters which have been developed. Again, I'm not going to get into the details of them, but they have been tried and some work in different situations. Then other people have tried to do the solution by designing what we call noise resilient architectures. So basically, you don't try to denoise them, you try to feed the raw images as it and expect the network to work around the problem. That is, denoise it or detect under the noisy condition and be resilient. So like many people have tried the solution, one of my students also wanted to look into that. And his approach was to find a solution which is in multiple stages. So I'm going to give you some observation based on his results. I'm not going to talk about his research itself in this talk right now. I encourage you to read the paper. If you don't have access to that, you can ask me for that. But what he observed was that if we take a model and train it in a mixed mode, where you take a variety of images, some noisy, some different noise levels, and different types of images, and then try to train the model, then it turns out to be more resilient. Resilience is defined here that the model will be working well under a variety of different input conditions. So the images may come from a variety of places in different modes, and still the system will work. And he found a good mix of this as part of his research result, and I encourage you to read this. But the challenge with this was that it took a lot of time to train that. So the question was, what else we can do apart from designing a robust network for a given application? Can we do better and use it on the existing models? So the answer is obviously designing a new model which will work. In this case, the new model was designed using a combination of old models and training it differently. But if you could design a right architecture for the system, that would be even better. And the method we want to use here is called the neural architecture search. And that's where the topic comes that we'll look for faster AI solution for this application domain. Whatever the methodology we developed here will also be applying to other scenarios as well. So let me quickly review the terminology of the AutoML versus NES. AutoML is automated machine learning, which you try to automate the task of applying the machine learning techniques to a real world problem. In this case, we were using the breast cancer detection. Hyperparameter optimization in this case is the taking a model and optimizing the parameters so that for the learning algorithm, so the solutions will perform better. And NES is a subfield of it where you're looking for a new architecture itself, or search the right architecture which is useful for the given application. And we are focusing on the NES part of it. So a variety of manually designed neural network exists. And again, many of you must have seen many of these names. I don't intend to go into details, just to give you the idea that a lot of people have been trying to work on this solution. And as you go from the left to right, take it back, your complexity of computation increases. And the models work better with larger amount of computing. Our goal is to find a better solution while keeping the computing under control. And more important problem is finding the network itself is a very compute intensive application. So that is a challenge too. So designing a new network is a very frustrating task because you need to decide how many layers, what kind of layers you will have, how to tune the parameters, and so on and so forth, and choose the best among the available choices. To motivate the problem further, let me give you an idea of what the complexity of this is. So you can see the NAS itself as designing a network itself is a network design problem. And so idea is that given a data set, you would like to an input-output pair, you want the network as the output. So we can think of NAS itself as an application and then find a solution for that. And that can find the solution for the problem. So that becomes a multi-stage issue. And the typical search element for this is that you will try to, as the name suggests, you're trying to look for some kind of a convolution network. So different kind of convolution operations, different kind of kernel sizes, different kind of filters, and it's a combinatorially large problem. How it proceeds? That you have a set of operations you can do on the given input data. And in this case, there's a normal convolution, dilated convolution, depth-wise convolution, point-wise convolution. These are all variety of filter operations which are possible in the system. You have, let's say, pooling operation where you say, how do you group the elements and work with them together? So I'm trying to take a specific example of a problem where I'm trying to design a network. And you can think about that a network might have two convolution stages followed by a pooling stage and followed by two convolution stages and a pooling stage. The intent of this slide is to give you the complexity of the problem. If you just want to do this and you have 4 types of convolution and 2 kinds of pooling operation, then you can come up with a large number of choices here. What convolution you want to use in the first stage, what do you want to do in the second stage, what kind of pooling you would like to use, and so on and so forth. An alternate solution will look slightly differently. It would use a different kind of convolution and different kind of pooling. So with only these many choices, in this case, the number of solutions you will have is 4 convolutions and 2 pooling, so that you have a total of 1024 combinations. You can look at each of this combination, evaluate it, how will it perform for this given input data, and then see which one of them is the best. So essentially, it's a selection problem, and exhaustive search is expensive. What you would like to do is to have some kind of factory arrangement where you feed all the kind of operations available to you, the kind of the data set you have, and then you come back and say, here is the solution. So that's like automatic production line. And that engine which sits in between is the neural architecture search solution. And that's the setup. So everything else rest is a black box. You give your input, possible operations, give you all the data set, and what comes out is a network. How do you automate that process? Well, in order to do that, we need to understand how the neural architecture search goes. So one methodology is the reinforcement learning, and second one is evolutionary. A reinforcement learning essentially is a loop where you predict a network and then you calculate the validation accuracy of that and then go and modify the network again. In an evolutionary learning scheme, you have a solution, you go make a selection, do some evolutionary operation. I'm going to give you an example. See whether that is fit for the solution, and then generate the next solution of your next evaluation. If you already meet the criteria of your performance, then you have a solution. Otherwise, you go back, try it again. So that's kind of, both cases is iterative approach. You keep trying the new one here. For the reinforcement learning, you generally will have an agent who is looking at the solution quality and gets a reward. And then it predicts the next solution that says how I'm going to revise my solution. And you can, in the agent-based approach, this is what will happen. The agent will decide what to do it. In a controller-based operation, there will be a controller which is predicting a model, and then you evaluate accuracy of the model, and again, try. If it's validated, that's wonderful. If not, you continue in the loop. So these are the two prevalent approaches which are used in this world. For the evolutionary architecture, it's like you apply some kind of a mutation. So you mix two things in order to get a third thing out of it. And the mutation result could be good or bad, will depend on how the output gets impacted. So again, you need to evaluate it for its correctness and accuracy. Here's an example how the evolutionary architecture will create a crossover. So it take two kind of species and create a new species out of it. Here are some examples. These pictures are from literature, so I'm not going to take any credit for it. It is just to motivate the problem approach. And the way it will work is that you have one solution on the left, you have a second model, and you design a crossover, which is taking some layers from the first solution, some layers from the second solution, and come back and have a new solution here. So in this case, for example, you took the first, third, and fifth from the parent one, second, fourth, and sixth from the parent two. This is one parent, this is second parent. And then you get the new output. The question is whether this will perform well or not. So you keep trying it. Well, where do you spend time is in this whole evaluation process. And in both these situations, you are looking at different combination, looking at the fit for it, accuracy for it, and that is where your time is spent. So in one example, for example, we could spend almost 40,000 GPU hours on an ImageNet data set to come back and say, here's the right solution. That's very expensive. So question was, how can we make it faster? Well, in order to do that, we wanted to understand what the impacts of different parameters is, and that some of the things which are used in the process are called pruning and quantization. Pruning is that you take a network and remove some other things from there. So keep a simpler model. Quantization is, do I need to do the operation of the 2-bit, 4-bit, 8-bit, 10-bit floating point, and so on and so forth. And combination of this will give you a new architecture for each stage. So what we really wanted to do, just to describe it before I go into the next set of slides, is that we said, once we come back with a new prediction of this is a model, can we evaluate it pretty fast? And if we can evaluate it pretty fast, then we can try a lot of choices and evaluate and keep discarding or keep accepting acceptable solutions and move forward. And in order to do that, and the goal here will be that you like to save the time, energy, power consumption, memory usage for the operation. So the methodology then goes that you're given a hardware platform and you have a search space where you're looking for a solution. You do either a design using a macro cell or cell basis, or a micro cell basis or macro layer basis. You have the objectives which will say you'll use one of these methods. And you have the hardware metrics, that how much time it takes if you do that particular operation on a particular set of hardware, what is the latency of computation, how many flops it uses. And you can use that data, and goal is to get the finally network solution using all these parameters. So this is kind of a block diagram of all the parameters which you need to consider in order to come back with the solution. If we can use some of the results which have been generated during this process and reuse them, that will save us time. And that is the approach we try to do it. So what we do is we try to look at all these parameters, and how do we go into design of a single cell. We start with a supercell where we say there are various choices to go from node K, K-1 to node K. We could use different kind of quantization method, different kind of pruning method. And question is which one we'll select. So we can try one at a time, or we can try all of them at a time and select the one which is going to work the best. So our approach was on this differential architecture search thing. Let's look for an approach where we can try with all of them together and select the actual answer based on which one likely to perform the best. And so this is simply become like the training the network again. It's a similar problem in that sense. So you start with a superset where you have all the choices on the left side in part A. You go and evaluate that, do all the mix operations of different kind. You start assigning a weight to saying which one of them is going towards the right direction. And then you come back with a solution, which is your final cell design. So it tells you exactly what model should you keep and what you should do away. In the process, you also learn which path generates what kind of computational complexity, what kind of latency, what kind of power usage, and start making a directory of them. We call that as a benchmark. So you start collecting these benchmarks as you are evaluating some cells, and then you start reusing that data. So all the intermediate results are somehow being captured and stored. And when next time when we come back with a predicted model, we can use them. And it's almost becomes like lucid, rather than trying to evaluating it using the actual computation, you can go and ask the benchmark a question that what would be the accuracy or the latency or the power consumption of this operation if I were to do this operation on this kind of hardware. So you're creating a table also as you're going along, and that's called the benchmark. The intent here is to go ahead and create a benchmark table and then use it for future designs rather than keep redoing the computation again and again. That is the approach we used here. So it is not something that it has not been done before. People have tried to do the state-of-art data, the benchmark right now, which exists, have been tried on a small set of data set here. Question is, what can we do about the large data set here? Our goal was to do the large data set, and we call it a once-for-all methodology, that once you solve a large number of models and create a benchmark, then I can use these benchmarks for future designs. And that's the intent here. That's what we call once-for-all methodology. And what we do with that is that once we have done that, I may start with a super network, the way I described earlier, and I take one sample of it and simply ask the question to my benchmark saying, what will be the answer for latency, computational efficiency, power consumption, and so on and so forth. Take another sample, do the same thing, another sample, do the same thing. But now this sampling will be running very fast because I'm not really actually training and evaluating the network. I'm getting these parameters from this benchmark. Actually, what we can do with the benchmark is we can create a surrogate model that now the benchmark data are fed into another neural network. Another neural network where I feed the current sample, and the network will give me the actual answer, like a validation accuracy in this particular slide, or the accuracy for one particular layer, accuracy for the second particular layer. So each time I start with a sample, I feed that into the network, I get the accuracy value. I take another sample, feed into the same network, and accuracy. So the methodology became that we collect the data for many of these evaluation processes, put them in a table, make a model out of that, and now any sample I need to evaluate of the network layer, I can feed that into that surrogate model and get the accuracy result. So this becomes more like a lookup table or a fast solution for that. And this surrogate models can also be used for the latency. So the same principle that you have surrogate model for latency, surrogate model for accuracy, and then you're using them to evaluate the process. So you are still evaluating a large number of networks, but your evaluation process itself moves very fast because of the benchmarking process and then using them for your evaluation of the network. So in effect, when you're doing a new network design, in this fitness evaluation step, which was the most expensive step in the computation for designing the network, you are essentially substituting it by an accuracy predictor and a latency predictor and use that as the metric. And this process then will move pretty fast because this step, which was slow, has become now faster. So compute one time, use it in future for other designs. And that's the approach we took here that led to a faster AI solution. So that's my pitch in general. that when you want to design, you should design a right network for the application you have in mind or hand, but try to design it effectively, correctly, and you can speed up that process itself. That's my conclusion for the talk. So I think that's about the time I have got. So if you have any questions, I'll try to answer very quickly. Otherwise, I think it brings me to my time.
Thank you, sir. Now, may I invite Dr. Dolly Sharma, Associate Professor, CSE Department, Amity University, Noida, to extend thanks to our keynote speaker.
So that was indeed an wonderful session. So one of the query that I have received from the participants is regarding the surrogacy model. Is it the best one for latency, or other models also do exist?
So the surrogate model itself will work as well as the data you provide to it, because this also is a model. So depending on how many computations you did and took the data and generated a model out of it, will give you the efficiency of the surrogate model. So it's like more data, more training you do, better results you get. Well, you can do the similar thing here, that more data you give to this surrogate model, better it will become in predicting it. So this is exactly the same problem as we started with. It's become an iterative process. And as you compute more and more, you can keep refining your surrogate model, and it will keep giving you better and better prediction. Will it work in all situations? Answer is actually no, because like a DNN model, it will work in most situations, but not in all situations. You want to make it robust, more data will make it more robust. So surrogate model is one of the good ones to approach. It basically saves time. That's the key point here. The new models can be generated fast.
Thank you, sir.
You.
So on behalf of Amity University, Noida, I would like to extend our heartfelt thanks for your exceptional keynote address, sir. We appreciate the time you dedicated for preparing and delivering such an informative and inspiring talk. Your willingness to share the knowledge and experience that has only enriched our event, but also left a lasting impact on everyone in attendance. So your insights, expertise, and engaging delivery has served a tremendous source of motivation to all the students present here and all the other participants. So with this, we conclude the session. I once again, on behalf of Fraternity of Amity University, Uttar Pradesh, thank Dr. Arun Samani for his significant presence and the wonderful session. We would like to thank all the students and participants for their cooperation. Thanks you once again, sir. Thank you very much.
Thank you very much.
Welcome, sir. Welcome, Dr. Lim.
Hello. Hi. Good morning. Hello. Can you hear me?
Yes, yes, sir. We can hear you.
Sure.
A very good morning to distinguished dignitary, respected professors, ladies and gentlemen. At the onset, I, Kriti, express a warm, respectful welcome to the 14th International Confluence 2004 Cloud Computing, Data Science and Engineering, organized by Department of Computer Science and Engineering, Amity School of Engineering and Technology, Amity University, Uttar Pradesh, Noida. As one of the leading global universities, MIT University is dedicated towards its responsibility of imparting its students with strong foundation and a platform for empirical inquisition. With this agenda, Confluence 2024 intends to bring together professionals, academicians, industry experts, researchers, enthusiasts to discuss various emerging trends and innovations, share results and new directions in the field of next generation technologies. Now, may I invite Dr. Dolly Sharma, Professor, CSC Department, MIT University, Noida, to present a sapling to our esteemed keynote speaker, Professor Dr. Chiping Lim, Professor of Complex Systems, Deccan University, Australia.
A warm welcome to Dr. Lim. May I please request you for the slide to present the sapling?
Ma'am, for this, I have to unshare first.
Dr. Lim, can we unshare your presentation for one moment? That would be okay?
Sure. Yep.
On behalf of Amity University, I would like to present a Tulsi sapling to you, Dr. Lim, on the online mode. Thank you very much. Thank you for being here.
It is our great privilege and honor to have amongst us Dr. Chiping Lim, Professor of Complex Systems, Deccan University, Australia. Professor received his PhD degree from University of Sheffield, UK in 1997. His research focuses on computational intelligence-based models and their applications. He has published over 600 technical papers, edited 6 books, and 15 conferences. He collaborates closely with researchers in the international arena with the support of numerous prestigious international fellowships. These include the Australia-India Senior Visiting Fellowship by Australian Academy of Science, Australia-Japan Emerging Research Leaders Exchange Program by Australian Academy of Technology, and Academy of Technology and Engineering, UK Commonwealth Fellowship, University of Cambridge, US Fulbright Fellowship at University of California, Berkeley, as well as visiting scientist program of Office of Naval Research Global at both Harvard and Stanford University. He is currently Professor of Complex Systems at Institute for Intelligent Systems Research and Innovation, Deccan University, Australia. I now invite our keynote speaker to address the audience. Please, sir.
Right. Thank you. Thank you very much, Dr. Dolly Sharma. Okay, it is really my great honor and pleasure to be here, this morning on the virtual mode. So without any delay, let me share my screen for some of the works that we are doing in terms of computational intelligence. Can all of you see my screens?
Yes, sir.
Okay. So this is what I'm going to share this morning. Okay, I'll just give a very brief introduction of what AI and particularly CI, which is computational intelligence, okay, is all about. Then I would share some of the works that my student and I have been doing over the years in designing intelligent learning models. And more importantly, okay, I'll share some of the applications that we have implemented for solving real-world problems. Right, so what is AI? AI is a hot topic right now. Okay, everybody is talking about AI. So according to the Oxford English Dictionary, basically AI can be defined as the theory and the development of computer systems, okay, that are able to mimic human intelligence. For example, okay, how we interpret images, how we interpret speech, how we make decisions, how we understand language, and etc. So if we could design, okay, a computer or a machine, okay, basically it's a computer that are able to perform, okay, all these tasks that requires human intelligence, that the computer system can perform as good as human. So we say that, okay, the system basically has that so-called artificial intelligence or AI. Right. On the other hand, what is CI? CI or computational intelligence is a term coined by Professor James Bestet in 1994. Okay, basically, okay, we can, or at least I interpret CI as a subset of AI, where we design algorithms or models that can compute, okay, with data. Basically, how do we process data? We use a pattern recognition component, and then we make sure that the system exhibits, okay, the characteristic of AI. For example, computational adaptability, fault tolerance, human-like turnaround speed, and etc. So in a nutshell, CI is basically computational intelligence algorithms that deals with low-level data by using some sort of a pattern recognition components or techniques. Right. And in 1995, David Vogel defined CI as the technologies of neural fuzzy evolutionary systems. And then they are able to adapt, okay, to new problems and do not really rely on explicit human knowledge, for example, if-then rules. So this is pretty much, okay, what my students and I have been doing over the years, okay, focusing on designing intelligent learning systems using neural fuzzy and evolutionary computing principles. Right, so I just give a very high and quick introduction of neural computing. Okay, basically it starts with the artificial neural network. So nowadays, okay, it becomes deep learning models. Okay, what it does is basically, okay, you have the input, you have the output, and then we have a number of layers, okay, in between. And the key thing is, okay, the neural network models is able to process, okay, low-level neuronal information, okay, basically data. If, for example, we open up an Excel spreadsheet, we see number 0 0.5, 1.0, and etc. We can make what is the what you call patterns behind all this data. So hopefully by using artificial neural network or deep learning models, okay, we will be able to see some patterns through clustering, classification, that kind of algorithm. Right. Fuzzy computing basically is a very nice model or technique, okay, that deals with linguistic vagueness and uncertainties, okay, which is very useful for human reasoning, control, and decision-making kind of applications. Okay, instead of, for example, we are saying that, okay, temperature, okay, 78 degree is warm, and then 78.1, okay, is very hot, or 77.9 is not warm, and etc. So we can have kind of a fuzzy membership function to say that, hey, 78 is about, okay, 0.2 in terms of the hot category, and 0.6 in terms of the, let's say, warm category. So you can see that, okay, the what you call fuzzy membership function doesn't really need to add up to a so-called 1. So it's kind of following the possibility theory rather than a probability theory. Right, another big domain of CI is evolutionary computing. So it perhaps starts with the genetic algorithm, which is a population-based kind of a stochastic search and optimization technique, try to mimic a human kind of a chromosome evolution by using mechanisms such as reproduction, crossover, and mutation. So the idea behind is basically survival of the fittest. So started with genetic algorithm. Now there are all sorts of computational evolutionary computing models like ant, particle swarm, bee. Okay, we have cuckoo search. Okay, we have the so-called wolf. Okay, gray wolf optimization. Okay, all sorts of swarm intelligence models are available nowadays, okay, to tackle mainly stochastic search and optimization problems. Right, so my research, okay, over the year actually focused on the so-called additive resonance theory. Okay, additive resonance theory started as a neural network model, and then later on, it includes the fuzzy principles to make it as a neural fuzzy model. So what we are trying to do is, or ARC is trying to solve, is basically the so-called stability plasticity dilemma. So which is termed as the holy grail of an intelligent learning system. So what this dilemma addresses is basically how can we design a database learning system that is stable. Stable means it can protect the information or knowledge that the system has already learned. And at the same time, it has to be plastic. Plastic means it can expand its knowledge base and it can absorb new information or learn new knowledge online. So we are contrasting the so-called expert system and the apprentice system. So what we are trying to do is to use this additive resonance theory or art as the principle to design a system that is able to learn from scratch and from zero experience. And then learning is basically perpetual, meaning that you can keep on learning online rather than relying on the current so-called train test kind of approach. So this is basically the key difference or advantage of app-based learning in terms of online or incremental learning. So this is the, as I mentioned, neural fuzzy. Started with the arts as a neural network model, and then it becomes a neural fuzzy model by incorporating the fuzzy principle, to design or to formulate this fuzzy art map network. And also we have other online neural fuzzy model as well, like for example, fuzzy mimex model. So the key characteristics or benefits that we would like to exploit by using FAM or FMM is basically autonomous learning, meaning that online learning without retraining. And also because some of the application that I have been working on is to do with decision support. So rule extraction in terms of explaining the prediction, or we call it explainable AI nowadays, is a key component. So this is a diagram showing how online learning evolves by using an app-based model. If you can see that the first what you call column with just 100 samples, and then if we can increase the number of samples online, learning one by one to 1,000 sample, you can see that the app model starts to learn the underlying patterns. And then if we can, go up to 10,000 samples, by learning more and more samples online, we are able to recognize or formulate the underlying patterns more accurately. So the difference between the top and the bottom is basically whether your data is noisy or not. So you can see that the learning actually is affected by noise in data. So noise tolerance is a very important factors that we need to take care when you use or when we design all these learning models. Right, so we have expand from unsupervised art to supervised fuzzy art models to semi-supervised art, where we combine the supervised and unsupervised principles in art, and then design and ensemble semi-supervised additive resonance model with explanation capability, meaning that to extract fuzzy rules for explaining the prediction in some of the publication, which was just by my student, which was published last year. Right, I will share a few applications of all these neural fuzzy evolutionary model in the next probably 10 minutes. The first is on the medical diagnosis and prognosis. So what we are trying to do is to predict different disease outcomes, for example, myocardial infarction, whether it's complication, whether it's trauma, etc., by using all these neural fuzzy techniques. So one case study that we have conducted is the prognosis of discharge conditions of stroke patients. What we are trying to do is to predict upon discharge a stroke patient, whether the patient would suffer from disability from minor to severe or even mortality. So the inputs of the neurofuzzy model is basically, very basic informations like age, sex, whether it's an alcohol, whether it's a smoker, it's an alcoholic, and also some test data. Okay, for example, the blood pressure, okay, the whether, okay, the cholesterol level, and etc. So what we did is, okay, we run through the data, and then you can see that, okay, the online learning principle allows, okay, the decision support. In this case, it's a decision support system, okay, to give, okay, more accurate predictions in terms of accuracy, sensitivity, and specificity when more and more test data, okay, or data is given, okay, for learning as well as evaluation. And more importantly is this so-called rule extraction, which exhibits the explainable AI principles, providing explanation to domain users. In this case, is the medical practitioners saying that, hey, okay, if a patient is predicted, okay, to have a disability upon discharge with a confidence factor of 0.8, then the next question is why? So we need to explain why is that, for example, age is high, and then etc. Low, high, medium, these are fuzzy terms. So we have the fuzzy membership function designed together with the medical practitioners. So this is a web-based model. Okay, it's just a very simple model demo. Okay, that I would like to share. So what we do is to conduct the training, which is online, and then when the patient comes in, okay, we punch in as many items, information, data as possible, and then the system will give a prediction. And as I highlighted just now, okay, the most important thing is the rules. Okay, the system not just give a prediction, but it also provides the explanation. Okay, this is very important in the decision support domain, especially in a critical kind of application like medical diagnosis. Okay, the user, okay, medical doctor would need to be convinced, saying that, hey, okay, the model is predicting something logical, something useful, rather than just simply give a prediction saying that, hey, this patient is a stroke patient, of probability of what. But I think rule extraction is basically the key thing or the selling point of this decision support system. And then moving on, okay, instead of predicting the health state, so the same thing, okay, we predict the health state of the machine. In this case, is fault detection and diagnosis of a power generation plant. So we collect, okay, for example, in the medical case, now we have the ECG data, we have the cholesterol information, age, and etc. Here we collect data in terms of pressure, in terms of temperature, sensor data from different points. So at the end of the day, when it comes to the additive resonance theory model, okay, basically it's just like a CSV file or Excel file. No, it's all about numbers. So what we do is, okay, for this particular application, we collected, okay, about 2,439 sensor records from 12 measurements of pressure and temperature at different points. And then the idea is to predict, okay, the blockage. Okay, there is a lot of piping system, okay, for cooling the power generation plant. So we want to predict whether there's any significant blockage or not, okay, in the piping system. So this is the small programs that we have developed, okay, for implementing the additive resonance theory based model for as an intelligent condition monitoring tools. So again, okay, the key feature of this is the rules that, okay, the system derive, okay, from the data set in terms of fuzzy logic. So when a warning signal is issued, okay, the user can retrieve the numerical number as well as the rule triggered, okay, by the alarm, okay, in order to appreciate or to understand why such alarm is triggered by the system. Right, moving on. Okay, this is another predictive maintenance of case study. Okay, in collaboration with a company in Australia. So what we are trying to do is to design a TNC, trust negotiation and communication, which is a multi-agent system to combine, okay, to use the federated learning principles to combine, okay, different data modality, for example, from signals, from images, and from text, okay, to enhance the prediction. And this is an example, okay, of the system that we work together with the train maintenance company.
We're getting 30,000 signals every 10 minutes. These are trains with brains. Turning that data into an insight, that's really the gold dust. We've built a platform with Microsoft called Train DNA.
We're using Microsoft AI to anticipate how much maintenance we're going to do and how much downtime is needed.
Train DNA is going to turn that information that we're collecting into something that we can use to improve reliability of trains.
So similarly, okay, it's a kind of a condition monitoring tools that we have developed for industrial application. And we also incorporated fuzzy into FMEA or failure mode and effect analysis, okay, to fuzzify the input in terms of severity, occurrence, and detection, okay, with the fuzzy rule base. And then we apply it not just to, big what do you call with big companies or okay in areas where we have a lot of data. Here we apply it to cottage industry in terms of bird nest production in collaboration with some small farmers and small producers in Malaysia. So, okay, we designed the fuzzy FMEA to provide systematic means of systematic methods for them to improve their process in terms of, what do you call, bird nest prediction, production. Right, and this is some of the current works that we are doing. Okay, we are focusing on various type of deep learning models from the classical CNN or deep belief network. We also combine it using a multi-agent approach. Okay, for real-world application of all these computational intelligence techniques. So this is a small case study of what we are doing in terms of image processing or surveillance monitoring in our campus, the Bow campus in Melbourne. Right. So I think this is a pretty standard application of CNN in terms of image and video processing. So our focus is to see how we can use the technique, deep learning model, improve it further, and then make it applicable for example, in autonomous vehicle and etc. Right. So last but not least, I just want to share a slide on how we move forward in terms of industry 4.0 to 5.0. So this is what our institute advocates, how industry 5.0 would look like. Okay, basically in a nutshell, we are envision that industry 5.0 would be an era where humans and machine need to work together, okay, seamlessly and then cooperatively to achieve the target of what we are trying to do in terms of automation, in terms of surveillance, in terms of safety, in terms of sustainability, and etc. Right. With that, I thank you for your attention, and I'll be happy to answer any questions that you all have. Thank you very much. Thank you.
Thank you for the session, sir. From the participants, we have received a question asking about other hybrid models that could be applied, like neurofuzzy models you have explained to us. Are there any other hybrid models that could be applied for the same?
Yep. So basically, the emphasis of at least my research work is on the so-called online learning. So adaptive resonance theory provides a good foundation in tackling the stability plasticity dilemma. So that's why we focus on adaptive resonance theory. Other online learning models, for example, Bayesian learning, Bayesian online learning models, Bayesian sequential evidence aggregation approaches, as well as like I also share some of the work on fuzzy mimics models. So I think the key idea is to focus on online or incremental learning kind of algorithm rather than the current deep learning, as well as, for example, neural network. Up to now, the deep learning, we need to collect SF data, we need to do the training, then we stop, we apply it to test, and then we go from there. But adaptive resonance theory online learning is basically the learning process is continuous. Every incoming data will be evaluated, and then it will be learned to reinforce the knowledge inside the model. So I think that is the key. So we are moving forward to see how we can improve the idea of online learning, make it more similar to how human learns. For example, we don't stop our learning process. We are not saying that, you have been learning for 10 years, you stop learning and then you start applying your knowledge. So our process of learning is continuous. So how do we create AI or CI models with this capability? So I think that is the challenge. So in terms of algorithm, if we focus on those who can tackle evolving data streaming models, I think that perhaps will be a good starting point. Thank you.
Thank you, sir.
Thank you.
Now, may I invite Dr. Dolly Sharma, Professor, CSC Department, MIT University, Noida, to extend thanks to our keynote speaker.
Thank you, sir. The session was really informative, and I'm honored to attend this session. So on behalf of Amity University, Noida, I would like to extend our heartfelt thanks for your exceptional keynote address, Dr. Lim. We appreciate the time and effort you dedicated for delivering such an informative and inspiring talk. Your willingness to share your knowledge and experiences has also enriched our event and also left a lasting impact on everyone in attendance. Your insight, expertise, and engaging delivery have served a tremendous source of motivation to all the participants. So with this, we conclude the session. I once again, on the behalf of Fraternity of Amity University, Uttar Pradesh, thank Dr. Lim for his significant presence. Big thanks to all the student coordinators for putting everything well in place, especially Atya and Kriti. We also would like to thank the audience for the patient listening. Thank you once again, sir. Thank you very much.
Thank you. It is my honor. Thank you very much, Dr. Dolly and the organizer. Very glad to be here this morning, and hopefully, we all can work together. And thank you very much. Thank you. Bye.
Thank you.
Yeah, that is not working anyway. All of you, can you please maintain silence? A very good morning to all the distinguished dignitaries, respected professors, ladies and gentlemen. At the outset, I, Shruti Mehta, express a warm and respectful welcome to 14th International Conference, Confluence. Hello, hello, check. 14th International Conference, Confluence 2024 on Cloud Computing, Data Science and Engineering, organized by Department of Computer Science and Engineering, Amity School of Engineering and Technology, Amity University, Uttar Pradesh, Noida. As one of the leading global universities, Amity University is dedicated towards its responsibility of imparting its students with strong foundation and a platform for the empirical inquisition. With the agenda Confluence 2024,
intends to bring together professional, academicians, industry experts, researchers, enthusiasts to discuss various emerging trends and innovation, share research results, and new direction in the field of next generation technology. Now, may I invite Dr. Rani, Assistant Professor, Amity School of Engineering and Technology, to present a sapling to our esteemed speaker, Professor Dr. Narayan C. Devnath, Founding Dean of Computing and Information Technology, Eastern International University, Vietnam. All of you, please give a round of applause. It is our great privilege and honor to have among us Professor Dr. Narayan C. Devnath, Founding Dean, School of Computing and Information Technology, Eastern International University, Vietnam. He is the founding dean of School of Computing and Information Technology, the Department of Software Engineering at International Eastern University, Vietnam. Previously, he served a full professor of computer science at Winona State University, Minnesota, USA for 28 years, and the elected chairperson for Computer Science Department at Winona State University for 7 years. Dr. Devnath has been the director of International Society for Computers and Their Application, ISCA, USA since 2014, and also served as ISCA president for 2 separate terms. He holds a Doctor of Science degree in Computer Science, a Doctor of Philosophy degree in Physics, and made significant contribution in teaching, research, and services across the academic and professional communities. He has published over 500 research paper and 15 books in field of software engineering, artificial intelligence and application, and information science, technology, and engineering. He has made numerous teaching, research, and invited keynote presentation at international conference, industries, and institutions around the world, and has been a visiting professor in different universities in Argentina, China, India, Sudan, and Taiwan. Dr. Devnath is a member of IEEE and IEEE Computer Society and a senior member of ISCA. Now I request Professor Dr. Narayan C. Devnath to kindly address the gathering with his words of wisdom. Please, sir.
Good morning. Good morning. Good morning. Don't look at your cell phone for next 15 minutes. This is not online anymore. If you look at the cell phone, then you miss the whole point because I'm going to show you something maybe important. You have all day for cell phone. Because of a little delay here, we have only 15 minutes. So we'll try to finish as fast as you can. Now, I saw many of you are just talking to each other, looking at the cell phone. Focus on this. Just open this. Yeah. Okay. Yeah, wait a minute. No, it's not working. Got stuck. Which one? Hello. Hey, can you hear me from the backside? Can you hear me from the backside? Hello. Can you hear me from the backside? Yes or no? Good. Let me tell you, the keynote is important, but not that important. So listen to this, some of the interesting one. Let's see where I'm coming from, the weather that we have. So originally I'm in the United States for a very long time, before you were born, more than 45 years. So this is where I used to live, the state of Minnesota, which is the Midwest North, very cold state, a lot of snow. This is the spring in Minnesota, beautiful. We have 4 seasons. Now, next is the summer. Look at this summer, beautiful. The difference between this is that the leaves are light green versus dark green. And finally, the fall is even more beautiful, which is this. You see, all the leaves are beautiful, and then they start falling. And when they fall, there is no leaves on the tree. So this is the late snow, the latest part of the year. The snow is about 4 to 6 months. Very cold, but beautiful. Okay, now, so this is the United States. Now I moved temporarily to Vietnam. This is how Vietnam looks like. This is my campus, Eastern International University. Here I am building a school of computing and information technology. Listen carefully, next few slides. It's a beautiful country and a beautiful campus. So this is Eastern International University. And as I said, I building a school for last 5 years, School of Computing and Information Technology. So you are welcome to come and join. And one important thing is, because it's a new school, I hire many faculty, academic positions from India in particular. So if you are, if you have studied computer science, computer applications, information technology, or related areas, feel free to come and join us anytime. So we accept a lot of applications and throughout the year, so there is no deadline. Particularly if you have a PhD in computer science, computer applications, information technology, computer networks and data communications, and communication technology, then this is the best chance for you. So if you know anyone who is interested to come to a foreign country to get a foreign experience, tell them to apply. A candidate who has recently completed or towards the process of completion of PhD is the best candidate to come. They will like. So take my email, and anytime you have, if you know somebody or if you are interested, come and join as a academic position. The best thing is international experience in a very good country, competitive salary, very good environment for work, and excellent research labs, AI labs, and also cybersecurity labs. So these are the good things to have. So anyway, if you are interested, if you know anyone, let them send the CV to me, and then we can go from there. Now the keynote. Keynote is very simple, not complicated like before. I will discuss only two things. What we know, that's the current advances, and what we don't know, that's the gives you opportunity and challenges. So everybody wants everything smart. You know, if you are keep on talking, then how can I talk? Ready? We want everything smart. Particularly, we want advanced intelligent medical and healthcare systems for accurate diagnosis and also treatment to save human lives. Most important applications that I see. And so the next thing is, simply speaking, we want intelligent devices and applications which really require intelligent software. That's all we have. Intelligent software systems. So if you want how to achieve, well, everybody will say AI, AI, and of course AI. Okay, yeah, and you all own everything that I'm saying, you all know. AI is a broad field for a long time. Started in 1954. Went ups and downs, ups and downs. So now that AI is very popular, don't overestimate, because you never know when it will go down. But as long as it's available, use it. So the subset of AI is a machine learning, which you all know, and the subset of machine learning is a deep learning. So these are, it says that AI, or in combination with machine learning and deep learning algorithms, it can do a lot of things, many applications around the world. And it's making a revolution, particularly in healthcare. So you can see there's a lot of applications in e-commerce, in navigation, agriculture, automobiles, gaming and sports, and intelligent transportation system, intelligent medical systems. In robotics, lots of applications. And you will probably see a keynote on this, that robot does many things and making things very simple. Then we have in terms of medical systems, sophisticated machines that can accurately detect diseases. And this is very important field to study. Particularly COVID-19 application. Normally the vaccine takes many years to come. But because of AI applications, probably it came exactly in 18 months. That was a miracle. That's how it saved the world. So we have all of those. And of course, there is a lot of applications in medical systems that you can see and you will know. There's many applications. There are 5 applications that we have is particularly one is robotic surgery and the other one is a chatbot. Those are the 2 very important applications. And these are all the detailed descriptions. We are not going into this. And so the important thing is the use of AI in healthcare industry is radically changing the face of information technology. That's where we are interested in. That we have a big role with AI to make something interesting and important. And of course, because of the AI spending is going to increase from 463 million US dollars in 2019, now will be over 2 billion in 2025. So these are the investments we are doing as long as the AI is alive. This is my AI lab, several projects. One is a traffic violation detection, social distancing alarm, and finally skin disease detection. This is AI applications that we are doing in different projects in the lab. So then remember that this is an important application that in the future, which is that in a hospital in Denmark, lots of brains they are collecting to examine. The idea is we cannot use them yet, but because it needs supercomputing power and advanced technological tools. And so what happens in this case, the researcher is trying to see that in the future, when we will have really the tools, we can analyze them and try to apply for a lot of important disease that we cannot cure now. Alzheimer is one of them. So the Alzheimer and dementia, the Parkinson's disease, these are the things that we can treat well if we can analyze those brains that we have collected. The next is a lot of advanced application like soft robot. It can change shapes and size as it moves. And then electric boats, then operating with holograms. All of these things probably cannot be done yet, but in the future it is coming up. So AI and machine learning applications to automobiles, to railways, to aviation, to healthcare industries are helping to significantly improve reliability, services, safety, and protection to human life and lifestyle. That's all we know. The question is, now we have two groups: computer users, like all of us, and second is computer scientists, some of us. So the question is, computer users believe we have everything, like you have cell phone. You have everything that you think you have. iPhone 15, beautiful. So you say everything you have. But the computer scientists believe, do we really get what we have? Do we really get what we want? And the question is unknown. And this is some of the things. Now it goes to the concept of software reliability, how reliable it is. That means how much it meets the specification. Okay, so that now goes to the software testing and all of those things. So let me quickly go through this. This is a software life cycle that you all know. Specification to design to implementation to testing and finally maintenance. And so if you look at this, each phase is not well developed yet, although this is 65 years old. So the question is, IEEE defines the definition, Bell Lab defines the definition. I have a definition of reliability, but eventually the goal is that does this really, any software that I produce, particularly large and complex intelligent software systems, which is very complicated, does it meet the requirement specification or not? So if we do that, it looks like that it does depend on accuracy of each phase. Some of the phases are well developed, some of the phases are not yet. Okay, so question is, can you get 100% reliability? The question may be, the answer may be the yes, no, or maybe. So there are many methods of reliability and validation of software. Testing becomes the most important one. So the most difficult part is progress in testing is very slow. Therefore, lots of opportunities for you to do for life. These are a lot of things that causes a problem for that we cannot achieve 100% reliability. One is we make a mistake in one phase and it propagates throughout the life cycle, making it very difficult. Then you have a lot of different types of faults, not just one kind. And there are some subcategories of faults also. So second, what we specify and what we implement, intersection is very small. Only 3 stages. Now, when we go into the testing phase, when you add that one, then if you look at this, only section which is meaningful is number 1. So we want to increase that as much as possible, because in ideal situation, all 3 circles should be 1. But the region 1 is very small, and the idea is how to maximize them. So keep on doing it. There are only 2 kinds of testing, functional testing and structural testing. Functional testing has problems of gaps and redundancy. Some we cannot test, some we are testing the same thing over and over again. And then, so this problem can be reduced or eliminated. Structural testing even has more difficulty. That means infinite number of paths that we cannot test. Infeasible paths we can never test. So phenomena like coincidental correctness, missing paths, all of those, these are impossible to solve. So now the question is, if these are the problems for testing reliability, then what is the final solution? So, so we have, again, three kinds of levels of design: unit testing, integration testing, and system testing. Unit testing has well-developed literature, but integration and system testing is premature. So these are the limitations. And so the idea is software testing, especially large and complex, is difficult. No acceptable methods, and 100% testing is impossible. That tells you that you'll have a job forever, and we can never say that a software is 100% reliable. So if we keep on going it, let's finish up because I'm almost over time. Can you achieve 100% reliability? The answer is no. Okay, so the field of software testing is wide open, leading to many challenges and exciting opportunities in the field of computational intelligence and innovative applications. And then through active national and international research collaborations, you cannot do anything alone. You have to do collaboration with industry, with other researchers in academics and all of those. And so we together can make a significant advances in a wide range of emerging intelligent software applications in the near future. So super intelligent AI is yet to come in the distant future. Thanks for your attention. On time.
Thank you so much, sir. Thank you. Thank you so much, sir. Now may I invite Dr. Rani, Assistant Professor, Amity School of Engineering and Technology, to present a memento to our esteemed speaker, Professor Dr. Narayan C. Devnath, Founding Dean, School of Computing and Information Technology, Eastern International University, Vietnam, as the token of gratitude. Everybody, please give a round of applause.
Try to take advantage of those. Listen to them, because you have to do a lot of projects in the future. This gives an idea how to get information. And then you can communicate with these scientists who came here from foreign countries. When all of these people came from so far to tell you what they know, and you're looking at yourself, well, what is it? I mean, you need to decide. They came here all the way to tell you what they know. And at the same time, you're talking to each other, you're looking at the cell phone. Yes. When you need to look at the system, they're all there. But this is very limited time, only 2 days of conference, and only few people travel all the way. Tell you what they know. So, thank you for your attention.
With this, we conclude this session. We hope that it was an enriching and informative session. I once again, on the behalf of Fraternity of Amity University, Uttar Pradesh, thank all of the guest dignitaries for their significant presence. We would also like to thank the students for their cooperation.
Danny, because I have another session.
Thank you everyone for your patience. It'll take a little while, but stay there with us. Okay, can I have all of your attention, please? We'll be starting. A very good morning to all the distinguished dignitaries, respected professors, ladies and gentlemen. At the outset, I, Jemima, extend a warm and respectful welcome to each and every one of you to the 14th International Conference, Confluence 2024, Cloud Computing, Data Science and Engineering, organized by the Department of Computer Science and Engineering, Amity School of Engineering and Technology, Amity University, Uttar Pradesh, Noida. As one of the leading global universities, Amity University is dedicated towards its responsibility of, uh, of, of imparting its students with a strong foundation and a platform for the empirical inquisition. With this agenda, Confluence 2024 intends to bring together professionals, academicians, industry experts, researchers, and enthusiasts to discuss various emerging trends and innovations, share research results, and new directions in the field of next generation technologies. May I invite Dr. Rani, Assistant Professor of MIT School of Technology, Science and Technology, to present a sapling to our esteemed speaker, Professor Dr. Abhinav Valada, Director of the Robotic Learning Lab, University of Freiburg, Germany. Please, ma'am. It is a great privilege and honor to have amongst us Professor Dr. Abhinav Valada, Director of the Robot Learning Lab, University of Freiburg, Germany. He is the director of the Robot Learning Lab at the University of Freiburg, Germany, and a member of the Department of Computer Science, the Brain Links and Brain Tools Center, and a founding faculty at the ELLIS Unit Freiburg. Dr. Abhinav is a DFG Emmy No Ether AI Fellow, scholar of the ELLIS Society, and the chair of the IEEE Robotics and Automation Society Technical Committee on Robotic Learning. He received his PhD with distinction from the University of Freiburg and his MS in the robotics from the Robotic Institute of Carnegie Mellon University. He co-founded and served as a director of operations of Platypus LLC, a company developing autonomous robotic boats, and has previously worked at the National Robotics Engineering Center and the Field Robotics Center of Carnegie Mellon University. Dr. Abhinav's research lies at the intersection of robotics, machine learning, and computer vision, with a focus on tackling fundamental robotic perception and state estimation and planning problems to enable robots to operate reliably in complex and diverse domains. His robot learning group has developed several innovative techniques for scene understanding, state estimation, and autonomous navigation that have defined the state of the art and ranked at the top of benchmarks. His group has also won several major competitions, and many aspects of their research have been prominently featured in wider media such as Discovery Channel, NBC News, and Business Times. I now request Professor Dr. Abhinav Valada to kindly address the gathering with his words of wisdom. Please, sir.
Okay, thank you for your patience and thanks for the introduction. So I'm Abhinav, I lead the Robot Learning Lab. For those who don't know where Freiburg is, I'm not sure if most of you know it. So we are on the south part of Germany, almost on the border of Switzerland and France. So very nice place. It's the biggest wine growing region in Germany and also the warmest weather in Germany. So this is how the city looks. This is the Black Forest on the back. And yeah, it's a very, very old city. And if you still want to know more about Freiburg, I encourage you to watch the Netflix series that's called Biohackers. And this was entirely shot in the city of Freiburg. So we are one of the oldest universities in Germany, was founded in 1457. And we publish a lot in AI machine learning conferences. We have one of the leading faculties in the world in AI, from robot learning, computer vision, machine learning, also in neurorobotics. So now let's go to the talk itself. So some of you at least would have seen this cartoon. Maybe can anybody guess which cartoon this is? No one? Okay, so it's Jetsons. So this is Rosie the robot, and this is in the early 80s. So since early 80s, we've been imagining a world, even in cartoons, where we want robots to come and do tasks for us. So these are like everyday tasks like cleaning the house or making food or, I don't know, teaching you how to dance, I guess. But if we look at today, like even after over 100 years, we still don't have robots around us. So it's kind of surprising, right? Like even after all these years of imagining robots, but we still don't have them. So why is this the case? So this is today. So this was a video that was shot a couple of years back for the Paralympics in collaboration with Toyota. And this is some of the tasks that we make our robots do. So we want robots to, again, do everyday tasks. So for example, as you can see here, picking up trash or I guess walking your dog or telling you how well you're working out at home, ironing your clothes, and tasks like this. So this is what we imagine our robots to do in the future. Or watch TV with your pet as well. So how do we get there? So what we need to do to get there is move from automation, which we can do really, really well, to autonomy is what we need to. So what does automation and autonomy mean? So what automation means, we want to do structured tasks in structured environments, and we want to program robots to do that. But what we want to do in the future is we want robots to learn by themselves from our environment without really programming exactly what to do. So we don't want to make the robots exactly program what to do, but we want to enable them to learn like how humans learn from the world around them. So I will show you some of the ways that we can do this, and we do this in our lab. So I'm going to talk about 3 things of how we enable robots to learn from the world around them. So the first one is learning from interactions. The second is embodied learning. And the last part that I'm going to talk about is learning both navigation, which means how to move around, as well as manipulation. So learning from interaction is very intuitive. So even us as humans, since as young as we are, people teach us how we learn to do tasks. For example, when you're a small child, your parents hold your hands and show you how to walk. And when you get older, your teachers teach you in school, like how to do math or how to do any other subjects. And for example, in sport, your coach also teaches you how to play a game. So similarly, with robots, what we want to do is we want to teach a robot how to do certain tasks in our everyday environment. So one way to do this is using a framework that's called learning from demonstrations. And what this means is that we train a policy, a reinforcement learning policy, and we collect some data, and then we train the robot on this policy. So just to show you one example, so here is a human, this is my master student. So now we're showing the robot, for example, how to open a door. And then from these example videos, then the robot first tries, it fails, and after learning after some time, then it learns by itself how it should open the door. So this is one way that we can teach robots, by showing them how to do something, for example, in videos, and then we can train them from these videos using a reinforcement learning policy. So there are other ways to also teach a robot from interactions. So the first one in the work that I showed you before, we show them videos, and then what happens in the real world is you can give a robot feedback. For example, like to say like, okay, are you doing the job well? Are you doing the job wrong? Or if you have a joystick, you can navigate the robot manually and then teach it from these interactions. So for this, we proposed an approach that we call corrective and evaluative feedback. What this means is that if you have a trajectory that if you want the robot to follow, and the robot first tries to do it, but when you see that it's doing it incorrectly, then you can manually joystick the robot into how it should do it. And by interacting with the robot this way, it learns by itself how to do. For example, this is a robot that's trying to, for example, close the microwave door, as you can see here. And here there's a human that is teaching it how to do it. And by correctly teaching it how to do it, then the robot learns by itself how it should perform these tasks. For example, closing the door. So I'm not going to go into details so much, but how this works is that, again, we have a policy that the robot learns. So we collect some data and we train this robot this policy on this collected data. And whenever you see a robot that's doing a task incorrectly, then you can give the robot feedback, and from this feedback, it learns to do it accurately. So we can teach the robot to do a wide variety of tasks. So these are tasks that we might do at home. For example, closing the microwave door, putting a lid on a kettle, plugging a charger on the wall, and so on. And we can also do this in the real world. So what you saw before is in a simulation. And in the real world, after learning in simulation, the robot is able to do these tasks in the real world by itself. Okay, so another thing I'm going to talk about is mobile manipulation. So what you saw, what most robots do today is in industrial environments, where I showed you a picture before, where these huge robots are fixed to the ground and they can't really move around. But in the future, as I showed you in the motivation video, what we want robots to move around in our environment as well as manipulate. So this involves two tasks that you want the robot to do. One is navigation, that's moving around, and the other one is manipulation, which is doing anything with the robot arm. So in the future, we want to do both of them together. So here we proposed an approach to train the robot to learn by itself how it should move in the environment, given a task that it should do for manipulating using its arm. So we train this again in simulation. So these are like simulated environments. So if you see these blocks moving around, that is to teach the robot to avoid obstacles, because if you have people, you don't want the robot to bump into people. So here the robot is learning in many different simulated environments how it should move around and how it should do the task. For example, here it's doing a pick and place task where it's picking up an object from a table and putting the object down in another table. And so these are all different tasks. So we train this using lots of simulation data, and then we are able to deploy it in real world environments. Now the robot has learned how to do these tasks. For example, again here, the robot has picked up an object and it's navigating to put the object in another table. And you will notice here that these are my PhD students. They will try to disturb the environment. For example, they will try to put obstacles, and the robot has never seen this environment before and it's not programmed to do this exact task. But then if you tell it to do this task, it's still able to pick and place an object, navigate in obstacles in a completely new environment that it's not seen before. And we can also do this with different types of robots. So this is a PR2 robot on the top, and this is the Toyota robot, the video that I showed you in the introduction. So here it shows you, I don't know if you can see it from there, but yeah, okay. So these are, again, different tasks, like opening a drawer or opening a door and so on. Okay, so another task that we want a robot to do is find things. So we as humans often lose things around us. We lose keys, we lose our phone. And if this is in our apartment, we want the robot to go and find it. So for this, we again train a reinforcement learning policy where a robot builds a map of the environment by itself. So this is the apartment it sees, and this is a map of the environment that it builds. And then it goes around and searches in this environment for things that you say that you lost. And not going to go into so much details, but again, this is a reinforcement learning policy. So what the robot takes as input is a camera image, a depth image, a semantic map. Semantic map tells you what types of objects are there in the environment. And then it trains a policy to then search for objects in the environment. So this is again in simulation where the robot is navigating in an apartment and it's trying to find an object. And this is, for example, a path that the robot takes to navigate and find an object. Okay, so again, in the real world, this is again the office environment. So what you see here is the floor plan map of the environment. And this is the robot that's navigating. This is a live image from the robot camera. And this dot here is the robot that's navigating to find objects that you see here, like green. And here, now the robot's going here. And so what it's doing is trying to find these objects in the environment. And one thing to note here is we have not programmed the robot to do this. So it's learned by itself how it should navigate and how it should find the objects on its own. So the video that I showed before, the robot's only navigating, so it's not manipulating the environment. So what if doors are closed? What if the objects that you want to find are hidden somewhere where the robot also needs to manipulate? So we extended this approach in a hierarchical manner. For example, we have low-level policies, for example, like avoiding obstacles. And then we have more high-level functions that you want the robot to do, which are opening doors, opening drawers, searching for things. So this is a hierarchical reinforcement learning policy. Again, the robot is now doing the same task, like searching for objects. And as you can see, sometimes when the door is closed, the robot's able to open the door or open the drawer and then search for these objects. So right now it's opening a shelf and then it finds the object that's inside. So we can do this again with many different types of robots. So here on the bottom, you see the Toyota HSR robot, like the same robot that you saw in the introduction video, in our office environment here in Freiburg. All right, so that's it for the talk. I hope you enjoyed this. I'm happy to answer questions if you have. Any questions? No? Okay, thank you.
Thank you so much, sir, for sharing your valuable insights on robotics. I'm sure it was an enriching experience for all of you guys present here. If you guys have any query, sir can maybe share your email. They'll send you via mail. Yeah. So you can visit his website and text, send him an email if you guys have any queries or questions regarding his session. So thank you so much, sir. May I now invite Professor Rani, Assistant Professor of MIT School of Engineering and Technology, to present a memento to our esteemed speaker, Professor Dr. Abhinav Valada, Director of the Robot Learning Lab, University of Freiburg, Germany. Please, ma'am. Yeah, can you guys please give him a huge round of applause? Thank you, sir. With this, we are concluding the session. We hope that it was an enriching and informative experience for all of you guys. I once again, on behalf of the fraternity of MIT University, Uttar Pradesh, thank all the guests and dignitaries for their significant presence. And we would also like to thank the students for your cooperation. Thank you all once again.
All of you, please be seated for 5 minutes, please. Volunteer, please ensure that nobody leaves the F2 seminar hall. All of you can leave now. If anybody wants to sit for next session, they can sit. If anybody wants to come for next session, it's at 12 o'clock. You can come. Students of CSE 3C, please, you have to stay here for attendance. Outset, I, Shruti Mehta,
And I, Jemima,
express a warm and respectful welcome to the 14th International Conference, that is Confluence 2024 on Cloud Computing, Data Science and Engineering, organized by Department of Computer Science and Engineering, Amity School of Engineering and Technology, Amity University, Noida.
as one of the leading global universities, Amity University is dedicated towards its responsibility of imparting its students with a strong foundation and a platform for the empirical inquisition.
With this agenda, Confluence 2024 intends to bring together professionals, academicians, industry experts, researchers, and enthusiasts to discuss various emerging trends and innovations, share research results, and new direction in the field of next generation technology.
It is a privilege and honor to have amongst us Dr. Gaurav Varshney, Assistant Professor, National Institute of Technology, Patna. Dr. Gaurav Varshney finished his BTech from UPTU and MTech at NSUT East Campus, Delhi in 2014 with a specialization in RF and microwave engineering and PhD at NIT Delhi in 2018. He is working in domains related to microwave, T-Hertz, and optical devices including antennas, fibers, absorbers, reflectors, waveguide, and transmission lines. He scored the specialization in dielectric resonator antennas, graphene antennas and devices, and metal-free frequency selective surfaces. Currently, he's working on quantum mechanics and nanoscale devices fabrication. Till now, he has authored more than 70 research articles in different peer-reviewed SCI journals, including Royal Society of Chemistry and IEEE. He is a reviewer in more than 60 peer-reviewed SCI journals. Now, I request Professor Dr. Gaurav Varshney to kindly address the gathering with his words of wisdom. Please, sir.
Yes, thanks everyone. Yes, good morning everyone. And thanks for calling me over here. Thank you. I think I'm audible.
Yes, sir, you're audible. So, will you be sharing a presentation or?
Yeah, sure.
Okay.
So is my presentation visible?
Yes, sir.
So thanks for calling me over here on this great conference, on this great platform for delivering my views on IoT applications. So as already discussed that This conference is based on cloud computing and related to some related parts. This point, IoT and applications, will be very useful for the people who are working in different domains of related to computer science learning and electronics and communication. So we must understand the basic concept of this IoT and applications, how it
Excuse me,
works,
sir.
and yes,
Sir, can you turn on your camera because it's not visible?
okay,
Yeah, thank you, sir.
is it visible now?
Yes, sir. Yes, sir. Thank you so much.
Okay, so point is how this IoT and applications, IoT is related to our daily routine life and how this is helping us in serving our daily routine works. So we can understand this basic concept in oral views, like we are having some central device like this laptop, and all the electronic and electrical appliances are connected to this single device, and we can operate all the different devices using this central device. So this is the basic concept that we can understand on the name of this IoT and how this is working. In a similar way, like if we go for the large arena systems, then in that case, this is ship, buildings, machinery, and some other vehicles, train, aeroplane, everything is connected through this IoT. This is Internet of Things. So if we see the basic mechanism of working of this IoT, so this is having 4-step process that we can understand. First step stands for collect RFID. So RFID is very important part, as we are the engineers of computer science and electronics department. So we must be aware of this RFID. This is radio frequency identification tag. Specifically, in my research group, we are working on the antennas, designing of antennas for RFID tag. Second step stands for communicate, and this can happen through internet. And next one is processing, analyze the data, will collect the information of the data through communication, and then we will go for processing analysis, and then we will operate and perform the function. So this is 4-step process that which is behind the operation of IoT. So the basic understanding of IoT, we can understand this is the simplest applications we have gone through a lot of times. This is some object like we had gone through different markets, and in stores, general stores, there is some device, and some electromagnetic signal is being transmitted towards this box, and some electronic chip is pasted on the outer wall of this box, and then this electromagnetic signal which is being transmitted using this transmitter device, this will interact to this RFID chip, to antenna systems, and then it will revert back some electromagnetic signal towards this device. In this way, we can understand what is the information of this total box. This information definitely will be saved in memory device of this. So if we see this concept, what is tangled with this chip, so this is the most important part we can understand. This tag, this is called RFID tag, and this tag is of two types. This RFID tag is of two types. One is the active type RFID tag, another one is passive type. In active type RFID tag, we simply place some battery sources so that it can generate its electromagnetic signal and transmit towards the receiver. Okay, and in passive type RFID tags, simply it will receive electromagnetic signal from the transmitter, and then it will receive that signal, and then information will revert that signal towards the receiver device, and information will be sent back. So here this is antenna portion, and if this is the central device which is connected to the reader, and this reader is connected to antenna, and then using this antenna we can transmit signal towards this RFID tag, and then we can receive it back, and then we can process it to find the information hidden in this. A similar process will be utilized for IoT applications. So basic concern of this IoT applications we can understand, like either connecting each and every device centrally, we can also connect all the devices within each other. Like this is something human connection, and this is having some controlling device. This controlling device is connected to some other appliances, and here you can see multiple machines are connected together. Means another purpose or motive of IoT is establish the connection between machines as well. It means one machine is operating another machine. Once connection is completely established and the machine is completely trained, perfectly trained, then one machine can operate another machine, like the robot system operating washing machine, robot system serving our dinings, robot system is serving the different home appliances. So in this way, machines can also be connected through IoT, and we must have the proper training of machine. So this is another example that we can consider, like there are two different machines and they are communicating each other through internet, and once they are communicating each other, then perfectly they can understand, read out the information, they can transmit and receive the information. After reading that information, they can perform accordingly. Like in this way, two robots are communicating each other. So this communication can be useful. One can understand this communication of machine will be useful for performing our routine works or daily works that generally consumes a lot of time. So if we see the IoT applications, there are a number of IoT applications. Right now we are working with building, home automation, manufacturing, medical sciences, defense, infrastructure, energy management. So many applications are there which can be governed with the IoT. So here the simplest example is the smart home service that we have, that we can design and we can just avail the facility. Like different applications are connected through a single device, like somebody is sitting in this room and can operate the machine of that particular room. The best example right now we are working with that IoT. This is Adrenox system. This is being provided by some car companies. Okay, like we are having some software in our cell phone, we are having internet connectivity, and we can operate that car, the different functions of car using our cell phone. We can open the door, we can close the door, we can open the sunroof, we can close the sunroof, we can connect, we can operate, switch on the AC, switch off the AC, and other parts. And if we are working with the concept of smart city and smart manufacturing process, so this is the another way, like this is the main thing that utilizes the human power. Here, if we see the communication must communicate, if we are able to establish the communication between machines using internet, then definitely these machines can work together and perform the related task of manufacturing. And this is the most required, uttermost required thing right now that we can understand in the agricultures or farming. The drone system, right now people are working with the drone system for this agriculture, for different activities related to agriculture and farming. sensing sensors are required for attaining the information of whether this, how much is the level of humidity of that particular area, how much is the temperature, how much is the required one. In fact, in the farming system, we can save the cost as well. Suppose humidity level is sufficient at that particular land area, then we do not need to spread the water body. In that case, we can save the water as well. In fact, we can improve the productivity of this land if we are having sufficient information about the land. Smart grid is the most fabulous concept right now. People are working. This power energy is definitely a concern of the researchers, of the community right now. The consumptions of the power must be deliberately defined. So in that case, right now we are working with the classical approach, like using transmission lines, the power is being distributed. But point is that how much is the power being consumed by particular station, it may not be restricted. In that case, the concept of smart grid comes into the picture, and it will act. Using this, the concept of a smart grid, one can optimize using some mathematical algorithm how much power is required as the user end, how much power should be generated at the source end, and how that power can be sufficiently utilized in different applications. So this is the one of the most important area right now researchers are working to develop the concept of a smart grid. And definitely if we are working with this the concept of smart grid, this concept of IoT can help us in saving the energy. If we are talking about our life, this IoT is the most familiar, most important thing. This is most familiar thing that we are working right now. This is the smartwatch. This is the concept of smartwatch. We can attain the information about our heartbeat, our body temperature. In fact, there are a lot of devices which are now available which can tell us about the diabetes level as well. And we can control our routine life, how much steps we have taken over in our full day's working, and how much we have to complete the task. We can assign. Specifically, we are working on the designing part of antennas already. I have discussed over here. So how this antenna works, I have few examples I had demonstrated over here in this slide. So this is the antenna which is placed on the wristwatch, smartwatch. So this is metallic antenna, and this is slot in that antenna. And challenge is we are reducing the size of the smartwatch. So how to adjust this size of antenna so that it can work on the similar frequency. Okay, so this is multi-port antenna system for performing the recent advancements or applications utilizing by recent advancements of the communication systems. We have to work with the higher data transfer rate. In that case, we must utilize this MIMO type of antenna, antennas with multiple ports. So this is one example which is utilizing multi-port antenna. This is our mobile case, and this is the antenna which is placed at the motherboard of this antenna. Okay, so we have challenged to just miniaturize the size of this antenna. And we have the challenge that all time we come up with some new applications, all time we come up with some higher frequency ranges to operate the cell phone, smartwatches. So definitely this wireless communication can be possible with the antennas only. So we have to design antennas daily according to the devices, according to the requirement of wireless communication. In fact, right now we are working with the IoT applications. This is very challenging to define, to design an antenna, to define the dimensions for IoT applications. Like if we are talking about tiny sensors placed in different devices, which are working to fulfill the IoT communications. In that case, designing antennas for IoT devices is further challenging task. This is another example of a smartwatch you can see over here. This is utilizing MIMO antenna. This is one antenna that we had designed in our laboratory. This is the case of electric resonator antenna having 4 ports, and this is providing radiation of power in this way. Red color portion shows the maximum of this radiated power. This is radiation pattern. So applying power at one port, second port, third port, fourth port, we are attaining the radiated power in different directions. Such antennas will be very useful for the devices, IoT devices, which are placed at our smart home services. Using at the central connections, we can locate our radiated power in that particular direction by changing the power of input port, and then in that case we can control the directional based coverage we can provide to this application. This is another example that we can place over here. This is tooth implantation of antenna. We can engrave with some sensor. This antenna can be engraved inside this teeth and human teeth, and then this can be accompanied with some sensing part. We can acquire the information of to find out the health of human teeth, because this is very important part, because we see in old age generally the problem remains teeth of most of the people decays or degrade, and we have to reimplant the teeth. This cannot be natural. In fact, human life is somehow related to the life of teeth as well. Okay, so if the health of teeth is correct, then in that case we can control our daily routine life as our age as well. So in fact, this teeth implantation can also be very useful for security or defense purposes. You can understand. This is non-destructive testing that we can go through. Like we had designed many pools, bridges. Right now this problem occurs, like bridges, their life is, the reliability can be on encircled with some doubts. So we can place some IoT sensors on different places on the pillars of these bridges, and we can understand, we can acquire the knowledge at how much is the vibration level, how much is the, if there is any crack inside that pillar, that we can understand, we can acquire that knowledge, information using data collected through IoT devices or sensors, and we can save our society. This was about our life. Now we can also talk about our friends' life. Like this is one problem. Like if we are talking about rhinoceros, this horn placed at the head of this rhinoceros, this is very costly. In fact, if we are talking about tuskers' teeth, these are very costly. So poachers do one thing, they cut their horn and these teeth, tuskers' teeth, and in that case they generally, this rhinoceros cannot give their its horn easily. We have to kill rhinoceros, means poachers have to kill the rhinoceros and they have to acquire its teeth. It's very inhuman activity that we can understand. We can place IoT sensors on the body of rhinoceros and elephant in different habitat centers, and we can acquire the information whether they are safely moving in the particular arena or not. This is one of the most important applications right now people are utilizing. This is about dairy products. We are having cows. We place some RFID tags on the ear of that cow, and using this is IoT devices, we can collect the information. The cows right now are moving throughout the city or in particular arena of forest, and at the particular time, like morning time and evening time, cows and buffaloes come back towards dairy, and they give our products and then again go back towards their daily working. So in that way, we cannot make them, we can make them free out of jail, and we can take help from us in form of milk and other products as well. So this is the another most fantastic application right now we are working. If you are walking around the city, you can see this is yellow color tag. This is placed in the ears of this cow and buffalo. So this is the most important and this is most familiar example of this IoT applications right now we are working. Challenges, privacy, security, and social harm. So this is the research gap, which is gap for computer science engineer, how to maintain the privacy, security, and social harm. Thank you. This is about IoT applications. We can work in that.
Thank you, sir. Anybody has any questions from sir?
Yes, I have a question.
Yes, ma'am, please.
Sir, I was listening to your talk. Within that, I noticed, if the field size, I'm talking about this agricultural application, if the field size is too small, and I say that I put in a drone there for, for smart monitoring and for sprinkle of all the medicine and things, how do we how do we justify, because at the present moment the cost of application or the cost of implementation is high, considering, because the scale has not grown so much, the applications or the drones are not so easily available. What is your point of view on that?
Yes, this is truth. Right now, cost is very high. If you are talking about drone, you are absolutely correct, ma'am. This cost of drones is very high. If we are going to deploy some drones and some IoT sensors or a small arena, like I have developed some sensors right now. So cost for approximately 5-meter distance is within thousands.
Yes, I got very small drone and that's costing me at least 4.5 thousand.
Yes.
Right. Okay, one more. If I talk of this smartwatch antenna thing, is this antenna working on first order radio energy model?
This is about wireless communication. Actually, you're talking about wireless propagation of the power. It totally depends upon linkage. Budget linkage defined for that. If you are talking about energy model, the antenna part doesn't have to do that. Like if you are a communication engineer, so you must tell directly how much energy you required, how much power is required. Antenna designer will set the goal. In that case, like how much gain of antenna will be provided. Okay, in that case, directivity and other parameters of antenna will be set in that sense. That will be defined by wireless engineers like you.
One of my student groups are working on making the smartwatch thing, and they are now in the process of printing the PCB, similar task as yours, that we want to minimize the size now. So what is your insights onto that?
This is recent challenge that also I had discussed about this. This is the point of miniaturization. In fact, you can call it like the size of cell phone is also getting thinner.
Yes.
So adjusting
How
antenna.
do you adjust everything
Yes,
within that small size?
this is the only challenge for researchers. So we can work. You are working fabulously if you are working on this smartwatch antenna. This is very fabulous. So
I
you
am
can
not into
extend.
antenna, you know it well.
Yes.
But we are into sensors part of it. I think we can work together on this.
Yes, ma'am, definitely, definitely. In fact, we can extend our working in mobile devices.
Right, right, right. Fine, sir. Thank you so much.
So thank you, Biva ma'am, for calling me. Already you are an expert in all these fields. I know this well. So still you had called me over here. Thanks for calling me over.
This was really wonderful. Over to Dr. Rani.
Anybody has any more else questions, like any queries? Anybody? You can raise your hand. Okay. We have one more question.
Sure.
Is this working? All right, great. Good morning, sir. Sir, I
good.
wanted to ask, as you mentioned that one of the challenges of IoT is the security factor, right? If we have every single device connecting to every single other device, and if there is a security flaw in any one device, and suppose someone could be able to control many devices with it, right? So, sir, what do you think would be the optimal prevention method in order to combat such a scenario?
Right now that we are working on QR codes, na?
Right, right.
We can provide individual QR codes, and we can establish some connections through QR code that we are also utilizing WhatsApp. Okay, like we are operating WhatsApp right now. Okay, and if there is a QR code connectivity, so individual one code provided will be provided to another device. So this may be a one prominent solution, but still there are glitches. So researchers are working to find that particular way so that QR code can also be very most impactful to that particular device. And in fact, this is the research goal that we have to establish some more secure purpose, secure technology too. We can work on it.
Thank you so much, sir, for your answer.
Anyone has any more questions? Okay. Yeah, so we one have.
Good afternoon, sir. My question is, as we know, IoT is dependent on connectivity. So how can we make sure that if one part of the chain is broken, so other part?
Yes, I couldn't understand. Your chain broken means there is
She's
a
talking about the fault
disconnectivity.
tolerance.
Sir, if the infrastructure is collapsed, so sir, another part
Hmm.
of the chain is broken.
Yes, we have to train the machine in that sense. Like once this collision or some distractions or disconnection is happened, then in that case, like if we had connected few machineries together, so in that case, one machine adjusts itself that how to establish another path. So there are two established mechanisms that we had understood in data communications or data structures already, BFS, DFS. Like if one node wants to communicate with another node, so there can be multiple paths. Ultimately, what can happen, like we have to search about the shortest path for the communication in general. But in case of disconnection happens during if one link is broken, so in that case, we can select another path using those algorithms. Direct first search, BFS, DFS, you had already started. We can optimize path.
Thank you so much, sir. Because of the time constraint, we cannot take any more questions, but we'll be definitely sharing your email ID to the students so that they can ask their queries to you.
Sure, ma'am. Sure. Ma'am.
Once again, on behalf of Amity University, we would like to extend a heartfelt thank you to Sir for taking time off his valuable, busy schedule and sharing your valuable insights with all of us. I'm sure it was an enriching experience for all the students present here.
With this, we conclude the session. We hope that it was an enriching and informative experience. I once again, on the behalf of Fraternity of Amity University, Uttar Pradesh, thank all the guests, dignitaries for their significant presence. We would also like to thank the students for their cooperation. Thank
Okay,
you.
thank you. Goodbye, everyone.
Hello, can you hear me?
A very good afternoon to all the distinguished dignitaries, respected professors, ladies and gentlemen. At the outset, I, Shriya Pathak, expresses a warm and respectful welcome to the 14th International Conference, Confluence 2024, Cloud Computing, Data Science and Engineering. Organized by Department of Computer Science and Engineering, Amity School of Engineering and Technology, Amity University, Uttar Pradesh, Noida. As one of the leading global universities, is Amity University is dedicated towards its responsibility of imparting its students with strong foundation and a platform for the empirical inquisition. With this agenda, Confluence 2024 extends to bring together professionals, academicians, industry experts, researchers, and enthusiasts to discuss various emerging trends and innovations, share research results, and new directions in the field of next generation technologies. It is our great privilege and honor to have amongst us Professor Dr. Bernhard Feringer. Professor Dr. Bernhard Feringer is currently working as a professor in the Computer Science Department of University of Waikato. He is also the co-director of the AI Institute, the faculty representative at the academic board, and the deputy head of the Machine Learning Research Group at Waikato University. He has 30 plus years experience as a researcher and has 269 publications till date where he has worked with numerous fellow brilliant minds in the field. His research interest and expertise lie in supervised learning, classification, machine learning, pattern recognition, text mining, data science, and artificial intelligence. He is a program committee member for various conferences. In addition, he has also received Spanish Government Travel Award for a research visit to the Technical University of Barcelona to do joint research work with Professor Gavalda September 2021. Now, I request Professor Dr. Bernhard Feringer to kindly address the gathering with his words of wisdom. Please, sir.
Good afternoon, everyone. Let me just share my screen with you. Okay, okay, now it might work. Let's try this again. Okay, and put it in the full screen mode. Okay, let's try this again. Yep. So I hope you see my screen, you see my slides, and you can hear me well. So thank you very much for this invitation to be able to talk to you about some, what I think are very exciting subfields in machine learning or AI in general. And I thank you for a very kind introduction. And I thought to start it off, I'll just kind of extend a little bit more on that introduction. So this is a maybe slightly unusual map of the world where New Zealand, where I'm based, New Zealand's up here. And of course, you know that you are here in the heart of India. So yeah, quite a distance. And New Zealand, as you can see here, is basically 2 islands and a few small ones. But Hamilton is kind of at the top of the North Island. And you may have heard about the Lord of the Rings and the Hobbiton. So this is actually quite close to where we are in Hamilton. So this is like 45-minute drive from Hamilton. This is just one of the nice sceneries that you can find in New Zealand. This is particularly on the South Island, but both islands have brilliant space. We are a small university. We've only about 500 academics and about 10,000 students, and we're also reasonably young. We've only started in '64, but we have a good reputation for research. And of course, also some of our teaching is, especially, we're pretty proud of our computer science degrees. And we have a nice campus on the outskirts of the city, and here in the back you can see the city. This is a small city, especially compared to your city. It's very small. It's about 200,000 people only. There's a lot of green and space there, which is nice. If you look at myself, you've heard a few things already. So basically, I see myself as an experimental machine learning researcher. So that means I like to build systems, but also like to evaluate and measure them to understand them better, and then maybe improve algorithms or come up with completely new algorithms. And I'm usually quite busy in the sense that I'm in the lucky position that I have many students applying. And so usually I have about 10 PhD students every year. And I'm also very lucky to be part of a large funded project called the TAO project that deals with environmental data in a streaming way. And so that's great to be in this position. And I'm also very lucky to basically only have to teach machine learning related things. So I teach an introductory course to machine learning, but also a more advanced one on deep learning. And if you look at the word cloud from my webpage and publications, it's very clear that it's learning and machines and data mining and yeah, lots of stuff around machine learning. So today, as I said, I'm going to talk about two subfields quickly. And I think it's important to look at those two because they actually have quite a lot in common. And currently, they're a little bit separated. So the first one I want to talk about is stream learning. So what is stream learning? I hope you've all heard about machine learning in general. But even if you haven't, basically in standard machine learning or batch learning, I've titled it here, you're given a data set, a training data set, and you have some test data. And the training data set might be a list of all the houses that have been sold in the last month and the price they achieved, and information about their location and how big they are and how old they are, and maybe lots of other things. And then you as the data scientist or machine learner, you can spend a long time if you have the resources to come up with a really, really good model that then is able to predict for any house that you ask for an estimated sales price, for instance. And it's not just houses, anything that you can select on, collect data on. Now, this is great, this works very well, and it's being used a lot, and it's very successful, but it has one big issue. And the issue is that things always change in the real world. So for instance, with the house price example, I'm sure the same is true in India, but in New Zealand, there are basically 3 different web pages where you can go to and type in an address, and they give you an estimate. And because house prices change over time, like the prices go up or they can go down as well, a model that you trained last year is out of date and might give you very wrong predictions. And so what currently happens in business is that most businesses that use machine learning models have to retrain them regularly, and sometimes quite often. So for instance, the house price web pages here in New Zealand, they retrain everything every week. So once a week, they have to do the same process again. Facebook, for instance, which is basically a machine learning company, even though they don't say that, they do retraining of everything very often, sometimes even multiple times a day, just to be up to date with everything. Now, the idea with stream learning is that maybe we can do something slightly differently to get away from this issue. So basically in stream learning, we assume that things can change over time. And what we want is we want to have algorithms that learn incrementally, and so improve a model over time, especially if the concept is stable and doesn't change, but also to be able, if something changes, like if you look down, here's an abstract example. I'm going to give you some more real examples a little bit later. If you had blue and red circles here, and there's a separating line that's almost perfect, if for whatever reason that line changes over time and the red and the blue are now distributed like that, your old classifier would be pretty bad. So you need to be able to adapt. And just in terms of giving you an idea of why this is important, everything you do these days generates data. So you basically leave a digital trace with every interaction you have with any kind of industrial system. And there can be, like down here, when we use public transport, when we have to pay, there's a record. If you buy stuff, there's a record. If you go to arbitrary web pages, there's a record. But also industry generates a lot of data. You've just heard about IoT before. There's a lot of sensors everywhere, and there's more and more sensors, or there's lots of cameras kind of observing traffic. And when you drive yourself and you have some system telling you where to go, of course, the system will also know where you've been. And so there's enormous amounts of data that are being generated. Now, I guess I will just probably skip that. Because we've already seen an example of that. So basically, the idea is that over time, things can change. And there's a lot of different types of possible changes. I might just put that out of the way for the time being. So you can go from one concept or one class straight to another. So we call that an abrupt drift. Or it can be very smoothly or incremental. But it's tricky because not every change is a real change. There might be just some outliers or blips or noise. So it is quite tricky to be exact in terms of determining drifts, but there are drift detectors that work really well if drift is really kind of consistent. Now, the other interesting thing is that when things change, you might also go back to something that you've seen before. Like a typical example is the differences in electricity consumption during the day, or between weekdays and weekends, or between summer and winter. And so you have trained your model in summer, it might not work that well for winter. So with a batch model, you would need multiple models. With a stream learning model, you might all the time just slowly adapt to what's currently happening. Okay, so drift detectors, luckily there have been quite a few that have already been developed. And so one that's being used a lot is this so-called ADWIN system, the adaptive sliding window. The idea behind most of these drift detectors is that you measure some quantity and apply some statistical test. And what you do is you have usually a setup with kind of two windows, one from a little bit in the past and the current window. And if you estimate something like the average electricity consumption, if this number significantly changes, and we have statistical tests to determine like that the mean has increased or decreased by a certain amount, then we declare that the drift has happened. And then our learning methods might do something explicitly to deal with that. And as you see, there's a couple of different names, and some tests are based on quite old statistics, like from the middle of the last century. And from this here, it seems that everything has been done in the early 2000s, but that's not 100% correct. There's still some interesting work going on in terms of people trying to come up with better change detectors, because they're really essential for what we want to do here. Now, if we look at stream learning methods, most of them are basically inspired by standard batch learning methods, but where someone has looked at the algorithm and tried to make it incremental, and also sometimes try to be already adapting to drift implicitly without knowing about it. And so for most of the methods, standard methods that you might have heard of in machine learning, like for naive Bayes, for decision trees, for random forests, and similar systems, there is a stream learning equivalent. Like for decision trees, we have the so-called Höfting tree. For random forests, we have the so-called adaptive random forest, and so on and so forth. And of course, it's not just classification. Same is true for regression and clustering as well. And to a smaller degree, there's also some work on like recommender systems in an online way. So all these methods are incremental. That's the most important thing. And either they implicitly, internally already can adapt to drift, or if there's an explicit drift event being detected by detector, we might retrain part of a model. So it is still retraining if you want, like with the adaptive random forest. If things change, the system looks at which trees are the bad ones and culls them basically and replaces them with new trees. Now, the other thing that's of course always important when we do machine learning is evaluation. We need to know how good our systems are. Now, in a stream setting, that's an interesting problem, but there's one simple idea that people have come up with, which is called frequential evaluation, or sometimes just called test and train. And the idea is, whenever an example comes in, first I use my current model to test, and then when I actually receive the ground truth information, the true label for this example, I will also immediately update my model with that. And again, we have variations of standard methods like cross-validation, there's a streaming version, and so on and so forth. And also, usually, we use the same ideas in terms of the metrics. So you look at accuracy, but also at precision and recall, sensitivity, specificity, and similar things. Now, to summarize that to some degree, the labels are, of course, important. And most of our research assumes that the labels will be available immediately after we made a prediction. And that makes it easy for the methods to learn. But this is not very realistic. That's a kind of a naive assumption. And so right now, there's a lot of work going on to build systems that are more robust to either not getting all the labels, so working with only partially labeled data, or having labels but with a delay. So for instance, if I have a system that automatically measures something and I do predictions, like something that's important for us is measuring river levels to be able to predict potential flooding events. If I predict the river level like for tomorrow, then tomorrow, 24 hours later, I have an actual measurement. I can measure how high or low the river level was tomorrow. And then so 24 hours later, I actually get the ground truth value. And now I can update my system. So there's a bit of a delay. And that is kind of relatively easy to deal with. But there's other cases where we may not get a label for everything, but only for a few cases, like sentiment analysis. You'd have to manually label everything, that's too expensive. Or if you do mortgages, for instance, a bank, if you approve a mortgage, then you will see if the customer is able to pay on time all the time, or if they default on the mortgage. But if you reject the mortgage, you will never find out if the customer would have been a good customer or not, because you just said no. So sometimes that's inherent in the process. That's an important current area. So this is like my 15-minute crash course on stream mining. Now we look at continual learning. That comes from a very different angle. Like almost 30 years ago now, Tom Mitchell, which you may have heard of, one of the founders of machine learning, and his then PhD student, who now is a professor and became very popular with automated driving stuff, Sebastian Thrun, they coined this term lifelong robot learning and then generalized it to lifelong learning. And so the idea was to actually look at how do humans learn? And if you think about it, very young kids just basically observe a lot of things and try to imitate that and get some feedback from their parents and from their friends and from their relatives. And then you go to school, and school is usually very structured, where like in primary school, you do simple things. Like if you look at math, you might learn how to add and multiply. And then later on, you might learn about algebra and geometry. And then even in high school, you might do calculus and differential equations. So you start with simple things and you build up tasks. And someone has come up with a very good schedule to go from simple to a little bit more tricky to really hard. But the idea is that when you do that, you never forget what you've learned in the past, so that you will always remember how to do addition and multiplication, even so you might be working on differential equations now. And then also maybe we might be able to generalize things. So like adding numbers, but then you learn how to add variables or something like that on an abstract level. And some of the tasks, as I said, will build on each other, but there will also be independent tasks. And sorry, sometimes we might also just be able to transfer some knowledge from one thing to a related similar thing. Now, if you're curious about continual learning, there's actually a really good webpage called paperswithcode.com/task continual learning. And a few months ago when I checked, they had more than 600 papers and also benchmarks and data sets. And this is the really cool thing, because data is the essential bit for machine learning research. Whenever you want to do something, you need to find good data to actually be able to experiment with. And if you have good data, you can do good work. If you don't have good data, it doesn't look so good. Okay, just a little idea. Often people coach continual learning in different ways. And so here we're going to look at examples that are just concerned with image classification. And there, often people like to talk either about task incremental, class incremental, or domain incremental continual learning. Task incremental is kind of the easiest, because we're assuming that, like in primary school, we're told now you learn additional, now you learn to distinguish between dogs and birds. And then a little bit later, next day, you'll be training to distinguish between guitars and ships. So that's the simplest setup. More tricky setup is if over time we just introduce new images, but not explicitly telling you, oh, okay, so today is only ships versus guitars, but we build up. And another scenario is where we still have the same classes, but for some reason, the quality of our images might change. Like here, we have a lot more noisy images. Or it might go the other way. We might get a better camera and we have much higher resolution images now and things like that. In the interest of time, I will skip that. But the interesting bit here is that it's not just the current accuracy, but we can also measure how much do I forget about old tasks, and how much do new tasks help me to maybe even perform better on the old task. We call that backward transfer, or forward transfer. How much will the current task help me to be better in future tasks? And that's kind of important, those ideas. Now, there's no good reason for it, but basically all of continual learning has only been working with neural networks. And so you find that most of the algorithms and ideas are developed around neural networks. Now with neural networks, one thing we know is that they have this issue that's called catastrophic forgetting. So if I've learned something and do that well, and then train the same network for something else, it will learn to do well on the new thing, but it will kind of completely forget over time the old task. Now, of course, continual learning is not what we want. And so people have come up with a lot of ideas on how to combat this catastrophic forgetting. And basically, if we look at it now, we can classify those different approaches into three groups. One group is basically just trying to make sure that the network does not change too much, which is achieved by so-called regularization. But basically, when you train for a new problem, you don't allow the network to quickly learn the new problem. You only allow it to make small modifications to the current network, but maybe over a longer amount of time. So lots of small modifications. But the hope, and that works to some degree, is that the small modifications do not completely wipe out the old knowledge. Now, a more direct approach is, of course, if we look at what we are learning now, if we keep some examples from the old task, and every now and then also mix them in to learn, and then maybe we can keep the old knowledge alive if you want. There's a number of papers around that, and basically the main idea there is to have a so-called replay buffer. So you somehow sample some of the examples that you're learning on and store them somewhere, and then later when you're working on the next task, every now and then you'll also look at your replay buffer and take some examples from there and just mix them in so not to forget. And the other thing or idea is to actually, because our networks are larger and larger, maybe we can kind of partition them so that some tasks work only on part of the network. And there's different ways of doing that. And sometimes we have one big network that's not allowed to grow, but people also have looked at dynamic architectures where you might be able to add like more layers or make layers wider in your network to have more capacity to learn for new tasks without forgetting about the old. And of course, now we can do all of that in a completely online way, because if you think about it, most of the deep learning is also batch learning. People look at data sets with 1 million or 1 billion images and just go through that over and over and over again, maybe even for a few weeks to get a really good classifier. But if you actually work in the real world, you might have a camera somewhere that's supposed to pick up animals or some whatever, and it's running all the time, and you want to do that continually. And so you actually want to combine the idea of stream learning and continual learning into something which is now called online continual learning, where the standard approach is using this replay buffer and just training a neural network, but mixing in old examples all the time. And there's probably too much math here, but basically the problem is with that is that we might not fit the new data well enough, and we might overfit the old data. So what we've been looking at is how can we deal with that? Because we want to have the old data, but we also want to learn the new data. And well, I have a very smart postdoc who's developed quite some interesting theory around that. But basically, the main idea is that we do a lot of training on mixes of old and new data, but we use augmentation, because augmentation slightly modifies the old and the new examples. And augmentation is the essential bit. So here in those results, the blue line is always without augmentation. And on the x-axis, you see the number of repeats that we do with every single mini batch for training. So if you do 20 repeats here, for instance, the blue line goes down, you overfit. Blue line goes down. The blue line kind of is stable, but you don't benefit. And here you might actually benefit a little bit. So it also depends on the data. Sometimes the data is diverse enough that it's not such a big issue. But here, both lines, the different ways of augmentation, you see, with augmentation, we get better performance, and usually you benefit from more iterations. And also, if you look at it, if you don't do the repeats, if you just do one repeat each, then the augmentation might actually make things worse. For this data set, definitely, and here as well. Not always, here already with 1 year better. So the idea is repeated training on the same buffers, but with augmentation. Now, another paper that, I think I can quickly go through that, tries something which is not using replay buffers, but where we try to identify important parts of a network and then assign them to one task and freeze the weights of that. And there's an additional complication here that we also try to detect the task automatically. And for that, we actually train autoencoders for every single task. So here we have the full network, and we train it on the first task. And then when we're finished with the task, we determine which are the important connections, and we freeze them, and the others are basically now available for the next task. The next task can use the frozen ones, but not update them, but also modify all the unfrozen ones. And so you do that for multiple tasks, and then here at the end, we have had 4 tasks. So you see, like the pink is what's essential for one task, and the green what's essential for another task. And we have 4 autoencoders at that stage. And so if we have classification problem here, with the autoencoder, we see for the first task, how good is the reconstruction? It's pretty bad. And for the second task, also very bad. For the third task, it looks quite okay. And we can see that here in the number. So this is a measure of error. The root mean squared error in this case. It's the lowest error. So it must be this task. And we use this part of the network to predict. It works pretty well, especially if you use a pre-trained network to generate features. That's an interesting bit of this paper that I can't go into much detail, unfortunately. So now with these 2 things, stream learning and continual learning. Now, if we look at it, what they try to achieve is stream learning just quickly wants to adapt to what currently is important, the current concept. It's okay for stream learning to forget about the past. Continual learning kind of sets itself a more difficult task. it wants to do well on the current problem, but also it wants to keep as much knowledge as possible from all the previous problems. And as we've seen in continuing learning, often we want to know what the current task is, so we want to explicitly being told. Stream learning has these change detectors that try to detect it automatically. But both of those assume that your data is not IID data. It's not identically and independently distributed. There are dependencies. So we've compiled a summary, but I don't have time to go into that. There's a lot of things that are similar and some overlaps. Now, basically, I should probably finish here now, also to give you guys some time to ask some questions. Here on the last page, I've just compiled a couple of recent references on papers that we have been successful to publish. It was pretty hard to publish something these days because there's so many people competing for spaces. And of course, we're also working on continuations of that as well. So thank you very much for listening, and I will open it up to questions now, and I will stop sharing my screen.
Thank you, sir. Does anyone has any question from sir?
Hello. Good evening, sir. First of all, I would like to be very grateful for your presence here and you enlightening us with all the knowledge that you have accumulated over all the years. Recently, I had the pleasure of being introduced to your work by one of my faculties, and I have been very intrigued, and my curiosity was piqued by your work. One of the questions that is very personal to me while I started this journey of machine learning and especially trying to figure out how the Hofding trees work was I came across the MOA OSS, which apparently you and your team developed at the Waikato University. So I was pretty curious, why did you feel the need to develop such a software in the first place?
I guess I'm not sure if you heard about that, but at Waikato, before that, we had already developed another system called WECA, which was basically a nice integrated system for batch learning. And what we have found is already with WECA, which inspired us to start MOA, is that if you have a software environment that makes it easy for you to add new algorithms or to modify existing algorithms, and if that environment also has built-in tools for evaluation, then you become more productive more quickly. And also, once you have that and you publish it, other people will pick it up and might use it and might extend it. So it might actually grow bigger than something that you yourself would have been able to do. And this is something that has worked really well for us in various regards. And what we've also done recently is, if you're probably aware that nowadays the main language for all kinds of machine learning is Python, but our MOA and WECA systems were all in Java. We now have a Python system as well, Python system that is called River. So a little bit bigger than a stream. It's actually a river. That's a little pun. And that also seems to be quite popular now. And the nice thing is, if you have this unified tools in your system for evaluation, then it makes it easy to publish and communicate. And so you don't have to manually always write some scripts or code to get some plots about your learning curves or whatever it is you want to look at. So I think that was the main reason for us. And also, sometimes, especially at the start, when you implement things, systems that have been published by other people, when you actually have to implement them yourself, you quickly find out that, well, you find out all the problems in terms of, have you really understood the paper? Because if you have to implement it, you need to make all these implementation decisions. And most of the time, many important decisions are listed in the papers, but not all of them. And so you also have to communicate with the authors of the paper, and you find out about all the interesting details as well. And generally, the students here also love to program. So that's a great setup for us.
Thank you, Professor Bernhard, to to hear your session. It was a wonderful session. And for further questions, we'll contact you through the mail. Thank you. Thank you all.
Okay, thank you very much. Thanks for having me. And I hope you all do a lot of machine learning in the future. Thank you. Bye-bye. Have a good day.
With this, we conclude the session. We hope that it was an enriching and informative experience. I once again, on behalf of the fraternity of Amity University, Uttar Pradesh, thank all the guests, dignitaries for their significant presence. We would also like to thank the students for their cooperation. Thank you. Have a nice day.
And after lunch, MCs proceed for the lunch, and students also enjoy their lunch. And after that, according to your session plan, according to your sitting plan, please be there.
Kindly.
Okay, thank you.
Very good afternoon to all the distinguished dignitaries, respected professors, ladies and gentlemen. At the outset, I, Lipika Walia, expresses a warm and respectful welcome to the 14th International Conference Confluence 2024 Cloud Computing, Data Science and Engineering, organized by Department of Computer Science and Engineering, Amity School of Engineering and Technology, Amity University, Uttar Pradesh, Noida. As one of the leading global universities, Amity University is dedicated towards its responsibility of imparting its students with a strong foundation and a platform for the empirical inquisition. With this agenda, Confluence 2024 intends to bring together professionals, academicians, industry experts, researchers, and enthusiasts to discuss various emerging trends and innovations, share research results, and new directions in the field of next generation technologies. It is our great privilege and honor to have amongst us Professor Dr. Domenico Talia, University of Calabria, Italy. Professor Dr. Domenico Talia is a tenure-track assistant professor at the Department of Electrical Engineering and Information Technologies of the University of Naples Federico II, Italy. He received his BSc, MSc, and PhD degrees in computer science engineering from the University of Campania, Italy in 2007, 2009, and 2013, respectively. He has held visiting appointments at universities in Italy, the US, Norway, and Spain, and has served as an associate and senior editor for several IEEE journals. He is currently the executive editor for the IEEE Communications Letters. His research interests include data fusion, network traffic analysis, statistical signal processing, IoT and wireless sensor networks, wireless communications, and machine learning. He has published over 115 plus journal and conference publications and is the co-author of the book Data Fusion in Wireless Sensor Networks, a statistical signal processing perspective. He has received several awards, including Best Paper Awards, an Exceptional Service Award, and an Early Career Technical Achievement Award. Today, he will be talking about distributed machine learning at the edge closed continuum. Now I request Professor Dr. Domenico Talia to kindly address the gathering with his words of wisdom. Please, sir.
Thank you for your introduction. I try to share my screen. I hope you see the screen on my slides. Okay, so thank you again. As you mentioned, I'm going to give a talk on distributed machine learning, discussing how cloud computing and edge computing systems may help to implement this kind of systems of application. So, you know, we are in in a age in which big data are assuming a very big role, a very important role. So, you know, we produce and exchange large amount of data every day, every second, every minute. You see that data never sleeps. So in every minute of the day, we produce a very large amount of data. So this situation of so rich data could be a problem because we are no longer able to read the data that we produce. So to read in this case, it means to understand how are important this data and how this data may help us. So we need intelligent digital technologies to understand and use the data that we produce. So that's why in the last 20 years, data analytics, data analysis, business intelligence, machine learning techniques have been proposed and implemented. Otherwise, it was completely impossible to handle with this large amount of data. Just to provide you with some numbers, you know, we are now in the era of zettabytes, you know. 1 zettabyte, it means 1,000 exabytes. That means 1 million petabytes and so on. Currently, perhaps in the world, there are around 1 or 200 zettabytes in our computers, in the internet, in our mobile device, and so on. So this is a huge amount of data. So big data are really big. And that requires technologies, algorithms, and solution, and obviously a scalable architecture to analyze this data and to extract from this data the important things that we need. So the so-called knowledge that we need. So to do that, we must be able to combine techniques and algorithms of data analysis and machine learning with scalable architecture that could be offered, for example, by cloud systems, by HPC computing infrastructure, and also, most recently, edge technology. So we need to combine this kind of infrastructures of scalable architecture to implement scalable data analysis and machine learning application. So, you know, we mainly at the moment are analyzing a large amount of data on cloud platform, okay? So this could be called machine learning or data analysis on clouds. But recently, what we need to do is to have also machine learning on edge devices. So more local, more close to us. This could be done also through the so-called federated learning approach. So we implement learning algorithm on different devices, and we put together the results of the local analysis to have a sort of distributed machine learning at the edge cloud continuum. So the goal here is to put together analysis both in the cloud, in the edge devices, and combine the results to obtain interesting knowledge, useful knowledge for us. So this is the approach that I'm going to present today. And to implement this approach, what we propose is to have an architecture based on these functions, on these functionalities, to implement such a kind of application. So, you know, when we think about machine learning algorithm, in particular in distributed systems, we need to separate the learning task that compose an algorithm, okay? So we must think in a distributed way to the algorithm. Then we need also to coordinate, obviously, the execution of these different tasks that are run on different computing nodes. So coordination in this case, it means exchange of information, exchange of data, exchange of partial and local results to obtain a global results. In this framework, we need also to manage failures, because some failures can occur in local nodes, or some failures may occur in the communication links. So we need to have algorithms that are able to manage with failures. They need to implement some sort of fault tolerance mechanism. So for this reason, the choice of an appropriate distributed algorithm to solve machine learning and data analysis problems depends obviously on the features of the problems, the configuration of the infrastructure environments in which the distributed algorithm will be executed, and also obviously of mechanisms for communication and synchronization among the different tasks that implement the machine learning algorithm. So including the use of edge cloud solution for distributed machine learning implies to involve the use of IoT systems, to combine the use of IoT systems with the use of traditional distributed systems. So together with cluster machine, parallel servers, or cloud infrastructure, we need to use also IoT systems. So here is a sort of four-layer architecture, very general architecture that we are using to implement our application in the edge cloud continuum. So as you may see, at the bottom layer, we have the so-called device layer, in which we have small size devices, mobile devices, sensors, webcams, and so on, that collect data, that filter data, that storage local data, and in some cases may implement some local learning task. So very simple local learning task. On top of the device layer, we have the edge layer that is implemented with edge devices that are able to aggregate data, to caching and filtering data, and also to aggregate some very simple model, very local model from the device layer. On top of this, we have the fog layer and the cloud layers. So this is the two layers that allow to implement collective machine learning, meta machine learning, and to store a large amount of data. So in this case, on these two top layers, we collect both data coming from the bottom layers, but also local models that in a sort of federated way can be aggregated together to produce global machine learning model. So this is the four layers architecture that we are using to implement our application. So as I said before, in the device layer, we have IoT devices, or small devices in general. In these devices, the basic data are collected. In some cases, data can be filtered, but mainly are stored, obviously. And in particular cases, this local data can be used to train local learning models that refer only to the data that a single device collects. Then, at the edge layer, we have gateways such as routers, base station, or micro data center that collect the data coming from the device layer, so gather the census data over IoT devices, reprocess some data, and implement some aggregation of local model learned from the many devices in the device layer. Then the results of this task can be sent to the top layer, so to the cloud or fog, both for storage purposes, but also mainly to perform complex learning tasks that obviously cannot perform at this layer, because If we have a large amount of data and we have complex algorithm, we cannot execute this algorithm, or we cannot manage this data at edge layer and the device layer, but we need to move to the fog layer and in particular to the cloud layer. So the fog layer is an intermediary and optional layer because in some cases could be removed if it's not used. That can be benefit from the computation that is closer to the cloud and more powerful than that provided by the edge layer and the device layer. So in this case, data can be stored and exploited for collective learning, for example. In particular, after the local learning on private data at the device layer, a collective training process can be run at this layer to obtain more complex knowledge, and in case this knowledge or the processes data can be moved to the cloud layer for the final learning process. So at the cloud layer, we have a sort of backbone of the network and a providers of persistence data storage. But at the same time, we have a very powerful and very large processing infrastructure that obviously cannot be offered by the layer, the previous layers. So at the cloud layer, we can implement large-scale federated learning algorithm and application. So we have a sort of global learning approach at this layer. So just to provide you one simple example to show how this kind of general architecture can be exploited and how we are using this architecture. If we look, for example, at a classification task, we may imagine that different elements of this classification task can be executed at a different layer of the architecture. So, for example, at the device layer, we can acquire the data from the environment through the use of a camera, for example. This data can be stored persistently in the device memory or can be processed to reduce its complexity. For example, this could be done through image compression. So the edge layer implements, in this case, a weak learner, so a basic learning model that can be trained on the edge devices using locally acquired images only. So in this case, for example, if we have an image with different animals at the edge layer, we can identify the different animals that are in an image. But this could be not sufficient because at the end, we would like not only to identify the elements of an image, in this case, the different animals, but also to classify them and also to learn about the complete image, so about the environment described by the image. So to do that, we move to the cloud and fog layer, in which the different local models can be aggregated in higher level. So for example, in this case, an edge server can aggregate only the models produced by the devices associated with it. So in this way, we obtain a partial model that can be combined by the cloud layer with the local models of other edge servers to generate an accurate global model. So in this case, this very simple case, we see how the different layer of the architecture operates to implement different learning tasks, and at the end, all the different learning tasks contribute to extract knowledge from the data, in this case, to identify and classify images. Obviously, the implementation of this kind of task, of this kind of application, through distributed algorithm, must take into account of different aspects, different issues. For example, one issue to be taken into account is data allocation. So typically in this case, instead of moving data where computation will be executed, we need to do the opposite. So computation must be moved as close as possible to the data. So because moving data may cost a lot, so it's better to execute the algorithm where the data is and not without moving the data where the computation is. So if a task cannot be performed on a certain node of a given level, support is requested to the higher level. So for example, tasks that cannot be performed on device are offloaded to edge nodes and so on to fog or up to clouds. So we need also to take into account of geographical distribution. So it's necessary to consider the geographical distribution of the hardware components that contribute to execute the distributed machine learning algorithm. This geographical distribution could be local, but could be also at very high scale. So in this case, the transmission of data could become a critical aspect. Other elements are, for example, the algorithm features and configuration. So each algorithm should be adapted differently to the others, and there may not be a unique way of migrating algorithms. Okay, so deploying machine learning algorithm in a sort of hybrid cloud edge architecture require to solve some complex problems, as there are many combinations of configuration parameters. So in this case, the most appropriate configuration could be identified. So finally, we have to deal also with task scheduling and the persistence of data. So in this case, and in general, when we have to deal with machine learning and data analysis application in a distributed environment, we need to have a sort of data-aware scheduler. So this kind of schedulers are useful to efficiently perform the task scheduling, considering the amount of data that each task must analyze. So the scheduler must ensure load balancing, must consider highly critical tasks, and, for example, must manage replication of data or replication of task during the execution. But the data-aware aspects is, I think, the most critical issue here. So the scheduler in the past considered wholly the task grain and the task complexity. Today, in the schedulers, we need to consider the data complexity and the data size. So the scheduler must be data aware. Obviously, it's possible to have also application constraints, and so it's necessary in the implementation of the centralized algorithm in this four-layer architecture to consider these application constraints. So functional and not functional constraints must be taken into account. So, for example, for this reason, machine learning algorithm must be configurable to meet the requirements that can be performed differently on the different architectures with different degree of freedom. For example, a less prices model on the edge node and a more accurate model on the cloud, because in the cloud we have much more computing and storage resources. So finally, coding and testing is obviously an important issue. So we need to consider that each layer could be implemented by different hardware and different programming tools. There are several today. there is a large research effort in this area to implement tools and programming languages for this kind of application. And we need to consider the different and the most appropriate programming environment when we implement our application. So this was just a presentation of this general architecture. To conclude my talk, I would like just to mention some open research issues that should be considered by people that want to work in this area. So, for example, some research area in which is interesting to invest, in which new results are needed, are as follows. So one is the availability of programming abstraction for big data analysis and for machine learning. So many people today use, for example, MapReduce, other use workflow model, but for the cloud continuum infrastructures, for the cloud continuum platform, others, scalable, adaptive, general, and higher level abstract programming structures and tools are needed. So this is a research area where a new solution must be devised and implemented. Another important research issues is related to data and tool integration and about the openness. So code coordination and data integration are main issues in large-scale applications that use data and computing resources. So we need standard formats, data exchange models, and common API. Then we need also to work in the area of interoperability of big data analysis and machine learning framework. So interoperability is a key issue here because we have to deal with data that are available from different sources, are geographically distributed, have different formats. So large and worldwide federation and integration of multiple data analytics frameworks and services are needed. So interoperability is another research area that is very important. So approaching the conclusion of my talk, we know traditional distributed computing approach to machine learning typically rely on the storage and the processing of big data in traditional large grain distributed systems. In this case, collecting data, querying data, analyzing data involves high communication cost that may be critical for low latency application. So this kind of approach are good for traditional infrastructure, for traditional architectures, but are not appropriate for IoT scenario, for edge computing scenario. So since the edge computing and IoT paradigms are emerged recently to meet the demand of processing data and producing machine learning results as close as possible to where data are generated, so we need to design and implement distributed systems for exploiting edge computing infrastructures. So for these reasons, a considerable effort in recent years has been made, is going to be made to adapt machine learning algorithms to perform cooperative training and inference on local data available on edge devices. Together with the adapting work, there are also activities for providing novel machine learning algorithms, so new ones that are totally different from the previous one because they are completely, totally designed for IoT devices and for edge devices. This is a very important effort that is producing interesting research results, but also important innovation in this area of machine learning in a very decentralized way for edge and IoT. So finally, the adaptation and the implementation of new solution of machine learning algorithm on edge cloud continuum architecture is generating a novel and interesting and useful scalable AI solution that exploit big data on this kind of pervasive infrastructures that today are very often used and that may provide important solution in many application domains. For example, in the medical domain or in the finance domain and the other important application domain where machine learning is largely used. So obviously, in case you need some paper on some information on this topic, I can provide you information on that. We published recently several books on these topics, in case you are interested. So I conclude here my talk, and I thank you for your attention. In case you have any question, I'm here to respond to your question. Thank you very much.
Thank you, sir. Does anyone have any questions for sir? You can raise your hand. No, no questions. All right. Once again, thank you, sir, for joining us. With this, we conclude the session. We hope that it was an enriching and informative experience. I once again, on behalf of the fraternity of Amity University, Uttar Pradesh, thank all the guests and dignitaries for their significant presence. We would also like to thank the students for their cooperation. Thank you and have a nice day.
Thank you. Bye-bye.
Thank you, Professor Talia, for elaborating such a nice topic, which is very in nowadays. Without cloud, we cannot access the data which we are using every time by socializing or by education media, technical media. So thank you for the nice session. I hope we will soon see you in the next year in the offline session. So
Thank you. Thank you.
for
Bye.
sharing your knowledge.
Bye.
For further query, we will contact you through the mails.
Okay. Thank you again. Bye-bye.
Bye-bye.
थोड़ा आगे शिफ्ट करा दो।
आगे शिफ्ट करा और जो भी सेशन हो एंड में मतलब 2 क्वेश्चंस तैयार रखो। After this, you are free. जब डमी क्लासेस अटेंडेंस मिलती है ना पूरे दिन, आज एक बार बैठना पड़ गया तो क्या होगा? ला लेना है मीटिंग, तुम्हें पता चल जाएगा। Please settle down fast.
A very good afternoon to all the distinguished dignitaries, respected professors, ladies and gentlemen. At the outset, I, Shriya Pathak, expresses a warm and respectful welcome to the 14th International Conference, Confluence 2024, Cloud Computing, Data Science and Engineering. Organized by Department of Computer Science Engineering, Amity School of Engineering and Technology, Amity University, Uttar Pradesh, Noida. As one of the leading global universities, Amity University is dedicated towards its responsibility of imparting its students with strong foundation and a platform for the empirical inquisition. With this agenda, Confluence 2024 intends to bring together professionals, academicians, industry experts, researchers, and enthusiasts to discuss various emerging trends and innovations, share research results, and new directions in the field of next generation technologies. It is our great privilege and honor to have amongst us Professor Dr. Cormac J. Srinam, University College Cork, Ireland.
Cormac J. Srinan is a full professor of computer science at University College Cork, UCC, in Ireland, where he has also served as head of department. Prior to joining UCC in 1999, he was on the research staff at AT&T Labs Research, Florham Park, New Jersey, USA, and at Bell Labs, Murray Hill, New Jersey, USA. At UCC, he directs the Mobile and Internet Systems Laboratory with research activity in multimedia and wireless networking and systems. Professor Cormac is a Science Foundation Ireland principal investigator and has published over 200 peer-reviewed papers, serving on several ACM IEEE journal editorial boards. His research interests include wireless network protocols and performance, including for unmanned aerial vehicles and for multimedia networking and systems. He is a fellow of the Irish Engineering Academy and holds a PhD in computer science from the University of Cambridge. Now I request Professor Dr. Cormac J. Srinan to kindly address the gathering with his words of wisdom. Please, sir.
Thank you very much. You can hear me okay? You can hear me okay, I hope. Okay.
Next time we will see you in the offline session.
Yeah, I'm just going to share my screen. 1 second there now. Now, you can see that? Great. Well, good afternoon. It's morning for me here in Ireland. Very chilly, -7, which is unusual. And thank you to the organisers of Confluence for the invitation to speak. Sorry I can't be there in person. I had certainly hoped to be, but circumstances permitted me, unfortunately, would not permit me to do so. So this afternoon, I'm going to speak to you briefly about edge computing. So a nice follow-on from the previous speaker. I caught the end of his presentation. And in particular, I'm going to tell you about some of my experiences of enabling artificial intelligence applications at the edge of mobile networks. Now, I suppose one of the benefits of being what you might call a senior member of the community is that you get to look back and see how technology has developed. So I want to briefly just talk a little bit about that, because I noticed just from the camera that many of your audience members are younger and students, and hopefully they might be enlightened somewhat by my journey. So when I started as an undergraduate, computing was quite different in the sense that the machines that we interfaced with were what were called dumb terminals. So no graphical user interfaces, no mice. And of course, this is a model in some sense akin to cloud computing, in the sense that all of the computing resources were centralized. They were in IBM or digital equipment mainframes. This would have been the 80s. That started to change with the introduction of things like the Apple Macintosh, desktop personal computers, and networks. The photograph down the bottom here was in Cambridge University, which invented one of the first local area networks, the Cambridge Ring. On the left is Professor Roger Needham, who's my PhD supervisor. On the right is Prince Philip. And up above that, there's some photographs of some interesting technologies that were developed in Cambridge at the time I was there. The first webcam pointing at a coffee pot. And above that is an interesting little box called Pandora that was developed at the Cambridge Computer Lab as part of my PhD, which augmented a personal computer with the ability to display video. So at the time, personal computers did not have sufficient processing power, so they were augmented by, if you like, some edge capability adjacent to the device. Moving forward, things shifted again slightly, particularly in industry and academic environments. People moved towards using high-performance workstations supported by centralized servers, primarily for storage, but also to some extent for processing. So this is a Sunray, which was what was called a thin client, right? So a device that has a graphical user interface, can display video and so on, but has very little processing capability. So here again, we have a sort of a shift to what eventually started, of course, to become cloud computing, where we have a mix of devices at the edge. Some of them are quite high performance, and some of them have very little computation at all and depend entirely on what's going on in the cloud. So I suppose when I look back, I see movement to and from the edge and to and from the cloud. And I think it's interesting to see how these trends develop and change over time. Now today, of course, and the previous speaker I know discussed this, we have what's called the continuum, the edge cloud continuum. This is a picture from the Gartner Group, which is quite well known, talking about the difference between the different kinds of edge computing and the distinction between near edge and far edge, with the far edge being closer to the end user devices. And as you can see here, the term edge computing then is quite a broad one, and it spans the kind of processing and storage that goes on edge devices, the kind of devices that you and I would carry around or have in our homes, right up to servers that are essentially look very much like cloud servers, except might be less powerful or located somewhat closer to the region in which they're operating. Now, the arguments for edge computing are interesting because they're very much driven by the needs of AI applications. So the first one being low latency. So many of the AI applications, particularly those involving any form of decision making, require low latency responses. So naturally, the laws of physics, by moving it closer to where the data is gathered, then you can reduce the delay in acting on that data. There's an argument that by keeping data close to where it's generated, you satisfy privacy and security constraints better. Obviously, if you don't transmit the data to the cloud, you're saving on bandwidth and data, and also, even though it's not mentioned here, the associated energy costs. It does, of course, raise issues with the autonomy. So by moving computing closer to the edge, in principle, you get more autonomy if links go down. In practice, that depends really on how things are designed and deployed. So I would say the motivation behind edge computing is very much driven by the need to enable AI. Now, in my lab here in Cork in Ireland, we've done a number of projects over the recent years that make use of the edge computing in order to enable applications which have some element of AI in them, right? So we have a number of projects. I have a different talk which looks at our work on connected vehicles. So we have a number of projects with companies and with Irish road authorities who are looking at the kind of edge computing that's needed to support connected and autonomous vehicles. We've done a number of projects using unmanned aerial vehicles which gather video and need to process that by sending it to edge servers. We've just started a project now with a large computer company to do this in an indoor environment in factories. And the third one then, which is the one I'll mostly be talking about today, is our experience using edge devices that are streaming video either from edge or cloud servers, and using AI techniques on those edge devices to improve the performance of video. So these applications tend to have a number of common themes: large data volumes, whether it's video or sensor data from vehicles, The devices are usually mobile, very much performance sensitive, and just from a practical matter, our interest is normally in focusing on 4G or 5G in terms of the delivery. Now, one of the things that I've always been interested in is if you're trying to enable AI at the edge, what are the different elements that you need to think about, right? I've identified in this slide what I believe are the 8 most important ones. And across different projects, we've looked at all of these in different ways. Data capture, pre-processing, real-time inference, privacy and storage, bandwidth conservation, resiliency, autonomy, federated learning, and model updates. In this piece of work that I'm going to tell you about today, that I'm going to summarize for you today, we focus on just 3 of these, right? Data capture and pre-processing, real-time inference, and model updates. We have other projects that look at the other 5 categories also, but just today, because of the naturally the limited amount of time, I'm really going to focus just on one particular project. And I'm going to tell you a little bit about that project, its origins, what we learned, open issues, and afterwards, obviously, I'll give you some pointers to our papers, and I'm happy to follow up separately. So this particular line of work is focused on throughput prediction at the edge. And we were motivated in this by the fact that many applications that exist at the edge can benefit from having timely and accurate throughput predictions for the performance of the cellular links. And the obvious one, and the one we've focused most of our work on, is video streaming players. So if you can predict the download or upload of its live throughput, then you can avoid stalls and you can improve what's called the video quality of experience. But there's lots of other applications that also benefit by having these accurate predictions. So in Industry 4.0, it can be for improving the determinism of sensor and actuator messages and behavior. For augmented reality, virtual reality, improving the perception of perceived latency. And for our work on autonomous and connected vehicles, scheduling and adapting the data exchanges. So there's quite a lot of applications that would benefit from this type of predictability. In our case, we focus specifically as an exemplar on network edge, but video specifically on the network edge, with the goal of trying to improve the quality of experience. This, I should say, this is joint work with a number of other people. Daria Raska, who is at the University of Sarajevo, a colleague here of mine in Cork, Ahmed Zaran, and several colleagues in AT&T Labs research in the US, in New Jersey, who have been collaborating with us in Cork on this work since we started it some years ago. So it's joint work from all that group. Our contributions across this project, and this has gone on now for about 5 or 6 years, we've been working on this area, are a number of different things. Firstly, looking at edge system architecture for enabling AI, the different practical considerations in selecting machine learning algorithms and how you use them. We're very interested, I guess, in systems aspects. I consider myself a systems person, so I like to either myself or my students implement and experiment. So we're very interested in how you implement these things on smartphones or edge servers, and especially in our more recent work, which I'll tell you about today, doing real-world experiments and overcoming many of the practical challenges that you really don't come across in theory or even in lab experiments. So I should say, even though the focus of what I'm mentioning here today is video and throughput prediction, we believe strongly that many of the lessons we've learned have much broader applicability for edge AI, not just specifically for video. But I chose to focus on video today because I think it's hard sometimes when you talk about these topics in an abstract way. And hopefully by picking this one particular exemplar, you get a better idea for how this works in practice. Now, the first thing I'm going to do is I'm just going to spend one slide talking to you about the way adaptive video works. And some of you are probably very familiar with this, and you can sleep for the next 30 seconds. For those of you who aren't, I'm just going to very briefly tell you about how adaptive video works, because it's important in terms of considering understanding the subsequent slides. Today, when you stream video, whether it's for Netflix or Disney or one of the other streaming services, or even if you use YouTube, it uses a technique known as dynamic adaptive streaming, or HTTP. And what this really means is that your video player requests video in chunks or segments, sometimes they're called, from the server. And it does this usually using a standard called MPEG- or some variant of that. It's widely used. All of the popular streaming services, YouTube and others, use some variation of this. The diagram on the right gives you a sense of how this works. So the video player requests these video segments. The requests usually go to some server in a content distribution network, which has been supplied by these from the origin server. The origin server has the video, it transcodes it into different bitrate variants. So it produces a number of different versions of the video at different data rates, some of them quite low, some of them quite high, and a selection in between. In some cases, there might be 100 or more different variants. It depends on the streaming company. These are then stored on the server. A URL is generated for every segment at every quality level and provided in this file called an MPD file, a media presentation file, which your media player then fetches from the server and uses it to decide to be able to identify which segment it wants to download. So as your player plays through the video, it's deciding each time what is the next segment I should get. That's usually the one that follows, and what quality. That's the key point. Right. So this picture here shows what a HAS, a HTTP adaptive video streaming player looks like. So the key thing in here is the adaptation logic. So the little box on the right is the adaptation logic. This is the algorithm that decides what video bitrate am I going to use for the next chunk, for the next segment, and then it goes and requests that from the server. It does this on the basis of some information that it gathers, possibly the buffer level. So if your buffer is getting low, it wants to fetch more quickly and maybe lower quality, so it loads faster, and also a bandwidth estimate. And that's really what we're gonna talk a little bit about. Now, this has been a major focus of research for at least 10 years, probably more. And if you look in the literature, there's lots of algorithms. Most of them are rate-based, so they're based on estimating the available bandwidth. Some are buffer-based, some are hybrids. The rate-based ones are mostly based on instantaneous throughput estimators. So they use well-known techniques like exponentially weighted moving average, arithmetic or harmonic mean, and others to try and estimate what the instantaneous throughput that is available as of now, and then uses that to fetch the next chunk. You might say they're reactive in nature. So if the instantaneous throughput drops, then it requests a lower quality segment. If the throughput goes up, it requests a higher quality. And in recent years, there's been a lot of interest in seeing, can you develop a better technique for making these estimators? And in particular, can you use machine learning? So way back in 2019, with our colleagues in AT&T, we did a what-if experiment to see if this was the case. So what we did was we did some real experiments using Google's ExoPlayer, which is an open source video player. And we compared two different things. We compared, in blue, the estimator that's built into Google's ExoPlayer, and in green, how the algorithm, how the player would have behaved if it knew exactly what the throughput is about to change to. And we have a number of plots here. I'll just go through them very briefly. So the top one is the buffer level, the middle one is the video bitrate, and the last one is the observable throughput. Perhaps the most interesting one is the buffer level one. So as you can see, the buffer level, this is in seconds, and for the most part, it's up somewhere between 20, 30 seconds, and then at around 200, the network capacity goes down. And you'll notice that with the blue one, the default estimator, the buffer level empties fairly quickly and it hits zero. And zero buffer level means a stall, right? So the video stalls and doesn't play. On the other hand, when you have the accurate prediction, you'll notice that it degraded, it dropped the video quality more quickly. You can see that in the middle plot, and as a result, managed to avoid until very much towards the end, for a very small period, it managed to avoid stalls. So this is good. So we felt this was positive. This seemed to indicate that there was a benefit to having predictions. Now, the problem, of course, doing predictions is the cellular network, the capacity varies considerably due to many, many different factors. And this is really why the throughput estimators struggle, because there isn't just one factor. There's multiple different factors that that affect how the network behaves. And we did some experiments on the bottom right here, measuring the prediction error with different existing techniques. And as you can see, the errors, you know, the 95th percentile is somewhere between 70% and 175%. And we these were using exoplayer and other techniques to compare. So in a cellular network, then with the existing techniques, it's very difficult to get accurate predictions. So we were prompted then to explore the use of machine learning. And I suppose the first question that one might ask is, you know, why machine learning? Why do we think this is suitable for this problem? And you know, when we thought about this, we thought machine learning approaches are good when there's a lot of data. Well, we have lots of data here. When the phenomenon can't be described analytically, we feel it would be very difficult to do that. And also when you want to look at multiple different metrics, so you have multi-dimensional space. And also, of course, when there is an underlying pattern, you can't predict if it's entirely random. So in our case, there are patterns. So there's a scheduler operating at the base station. It's a black box. We have a pretty good idea of how it works, but it's not published. It's something the vendor keeps to themselves. Patterns due to channel conditions and patterns due to user and application behavior. So there are patterns there which we would hope to be able to extract by looking at a multiplicity of different performance features. So our approach then, and this is similar to the diagram I showed you a minute ago, our approach here is to augment this by replacing the prediction engine by inputs from radio channel measurements. So these acronyms here, I'm not going to go through them. These, this is actually our work on LTE. These are different radio level metrics for LTE, and also velocity and throughput. So combining all of these measurements together, providing these to the prediction engine, which uses machine learning techniques to provide a better predicted value, which can then be fed to the adaptation logic. And in some of our papers, we also experiment with how exactly to integrate these predictions into the player itself. Now, one of the things that you look at here in terms of edge AI is what the architecture is that you want to use. The diagram on the right is a bit complicated, so let me walk you through it. Fundamentally, there's three different tasks here. There's data collection, there's training, and there's predicting or inference. And these are the TP, the throughput prediction components. And there are options for each of these, right? In particular, you know, for collection, data collection, it's useful to consider collecting data on the device itself, but also possibly at the base station. And for training, you might do training on the device, you might do it at the base station, in the cloud. And equally for predicting, the same thing. Do you do this on the phone or in the cloud? And we considered a number of different architectural options. Number one below is the one that we use in most of our experiments, where we collect data only on the phone. We train in the cloud, but we do inference on the phone itself, which means very low delay on the phone. Another architectural option, which we have evaluated, but this one only in simulation, is to use data from the base station as well. And all of our experiments show that that gave a much higher accuracy by having that information as well as the information from the phone. There's some practical reasons as to why that's challenging. So our architecture then being defined, we moved on to do a number of experiments, and we've published a lot of work in this area. Most recently, which is what I want to tell you about now, this work will be published this year. We moved on to look at real-world challenges. So we led the field in this area with experiments in the lab and trace-driven experiments. When I say traces, we gathered lots of traces from 4G and 5G networks. We've published these, actually. They're quite widely used, and they're available to any of you if you want to use them in your research. And one of the things that we observed was that almost every paper in the literature was using trace-driven studies. And the models were trained using these trace-driven studies, but also using saturated network links, so large file downloads. So virtually all of the traces were gathered by phones downloading large files. And one of the problems with this is that video doesn't behave like large file download because you have periods of on and off. So video players, they're on when they're downloading video, but then they stop and they look at the buffer and they look at the estimate of the throughput, and they might say, I'm going to stay turned off for a while now. So the link is not saturated. And this makes it much, much harder. Two things: one, to predict the throughput, but also to measure ground truth, because you might be measuring low throughput, but that may be because the application isn't actually downloading. So we set off last year to do what's called an in the wild experiment, where we actually implemented machine learning on an Android phone and did experiments in multiple operational networks. And I'm going to talk about a couple of the challenges and a couple of the contributions. So one of the challenges is in terms of the file download problem. So that I just mentioned. On the left here, we see a plot showing the distribution of throughput for whether you're doing file download or video segment download. And as you can see, they're quite different distributions. The video segment download tends to be much more focused on smaller segments. The file download is distributed right up throughout a much larger range of values. Another practical matter was the APIs differ for actually reading things like signal strength. And not only that, but on some devices, the updates are not available very frequently. Labeling the data so that you know when the actual application is active turned out to be an interesting problem. And again, all of these are problems for other machine learning applications on edge devices, not just this one, but we're just highlighting it for video in particular. So we saw things like, you're trying to figure out whether the video is active or not. And you also, in practice, get missing values, right? So when you're dealing with real devices and real APIs, sometimes you don't have the data. And the plots on the right show the impact of missing data. So you can see things like, if you look at the plot on the bottom, for example, which is the absolute relative error, when you have 80% of the data values, your errors are less than 20%. And when you're down to maybe 40 or 20%, your errors jump up quite significantly. So in practice, you don't always have the data on a continuous basis that you would like. One of the main challenges we had to face was distribution shift. So this plot on the right shows a measurement in the same location at the same time of day, but different days. And you can see the distribution as measured is quite different. Now, this was using file download just for simplicity. What this means is that the distribution that you're reading that you're looking at is changing. So if you've trained a model on this data, for one day or for one series of days, you're likely to have to allow for the fact that you're going to have to update it over time. So our system, and I'll give you a reference for this later on in terms of the paper, our system basically, it's implemented on Android. It has a thread on the right, which is responsible for collecting the metrics and monitoring the activity, so trying to infer when there's an on or an off period. Doing some pre-processing of the data, and then on the left-hand side, the actual adaptation algorithm. We use a deep learning model. We use a shallow model because we found that it generalized and helped us with the distribution shift, but we also then augmented it by transfer learning. And so, yeah, so the reference for this paper, if you want it, it'll appear later on, is down the bottom of the screen here. So our experiments were using real networks across 3 different countries, the United States, Ireland, and Bosnia, with a range of different videos using the Android video player and using a selection of videos from our own published repository of videos, which has videos across 13 different video representations. There's a lot of results in the paper, right? And this being a keynote talk, I'm not going to go into detailed results or details of the system, but I do want to give you just example results, just hopefully to give you a sense for what resulted from this effort. These 2 plots, the one on the left is the average bit rate in kilobits per second, and the one on the right is the number of switches. What switches means is a switch between different quality levels for the video, so from a high level to a low level or vice versa. And the C1, C2, and C3 represent the 3 different countries. And so this box plot on the left-hand side of each is the default behavior. This is using the Google's ExoPlayer default algorithm. On the right is our deep learning algorithm. And remember, these are experiments on real networks, so they're not as clean and neat as you would expect in simulation or lab experiments. But broadly speaking, you notice 2 things. The bit rate generally is higher and less variable in the predicted case, and the number of switches is lower and less variable. So the number of switches is important because this affects the user quality of experience very significantly. So what did we learn in this work? So I suppose we set out to look at throughput prediction as a exemplar AGI application, but particularly to consider the practical problems. Our implementation showed up a number of problems that were not evident otherwise. So problems that we hadn't really seen reported in the literature because most people were working on lab or trace-driven data. So determining accurate ground truth, access to metrics, radiometrics, labeling the data, dealing with missing data, and practical problems that are really important for your training. And then finally, distribution shift and the need to be able to support model updates. What we found, I suppose, in terms of the machine learning side of things, is the combination of shallow models and transfer learning proved to be a good way of improving the prediction accuracy and, as a result, improving the quality of experience. But this is, I would still say, even though we've been working on this problem for a number of years, a lot of additional work is needed, including possibly exploiting federated learning on the edge for distributed learning so that the different devices can actually share their experiences with each other. So thank you for your attention. And I suppose I should acknowledge my sponsors, Science Foundation Ireland and the Connect Centre. So Connect is a national centre in Ireland for future networks. I'm one of the deputy directors. It's a large-scale centre, about 300 people. And this work was part of the Connect activities. So thank you very much.
Thank you, sir. Does anyone has any question here? Yeah, you may ask.
Afternoon, Professor. Actually, I was a bit curious. We have been using edge computing for big data analysis and all that. But how is it that much significant if we are talking about video streaming and all?
I might try and clarify your question if you don't mind. So are you questioning the volumes of the data? Is that it, or why the problem is different from big data analysis?
The main issue was that edge computing was generally used for big data analysis. But when we are talking about tasks like video streaming and all, what is the significance of edge computing in that in general?
Okay, yeah, so yeah, I mean, obviously the volumes of data when you're looking at data measured from a cellular network are, while they're still significant, they're much smaller, for example, than images or video, for sure. I suppose the significance is that you require low latency responses, right? So if you're doing prediction for throughput, whether it's for video or augmented reality or something else, latency is crucial, right? So this indicates that you probably would want to do the inference, at least at the edge. Now, whether you do that on the edge device itself or whether you do this on an edge server, I think is open to debate. I hope I'm answering your question. If I'm not, feel free to elaborate.
Okay, thank you, sir, for the wonderful session. So I hope we will see you in the next conference in the offline mode. And as we have to move for the validity session and for the further queries, we will contact you through the mail.
Thank you very much. Goodbye.
Bye-bye.
With this, we conclude the session. We hope that it was an enriching and informative experience. I once again, on behalf of the fraternity of Amity University, Uttar Pradesh, thank all the guests and dignitaries for their significant presence. We would also like to thank the students for their cooperation. Thank you and have a nice day.